how we could serve the Earth observation community and what sort of calibration services we should add to the site. And yeah, so we are at this stage we are not yet actually active, but starting from next summer we will have something working there. So the site is here in Syökulla. It's about like 25 kilometers west from here at Kirkkonummi, and so it has been operated by the FCI since 1994. It has been originally meant for airborne remote sensing system calibration, and today it's also a drone permissive test area where we do most of our drone testing, and also collaborators can be there. And yeah, it's like 25 kilometers west from here, and another like key site close to it is the Metsähovik Geodetic Core Station, where we can have some sort of like permanent staff and active services in there. So, but like the first question is that why should we have a optical satellite Kalevala site in southern Finland? Most of these sites that are used for primary calibration, they are some sort of desert sites, very large and placed in very clean atmosphere conditions, and those are objectively they are better for absolute calibration of the systems. But what we can do here in like southern Finland site is that firstly the satellites visit us more often, so we can actually have more calibration occurrences. Then also a negative thing about being up north is that it's only like usable only for 6 months per year. Possibly SAR images could be calibrated also in winter time, but that's a bit questionable thing. But the atmosphere is actually not that bad in here. So based on some data that we have found is that basically in the summertime when the site is usable, about 50% of the daylight hours are actually sunny and clear that can be used for calibration. But basically what we are specializing in is not for the primary calibration of these satellite sensors, but it's more like a validation, and especially validation of bottom of atmosphere products in atmospheric conditions that actually match the applications. So that it's not really useful to do validation of your data quality in clean desert conditions if you're actually measuring things in places like in Finland. Yeah, so as I said, the site has been there already since 1990s, and it has been continuously renewed a little bit, but there's some it wasn't in perfect condition in last summer, so we did a study of what are problems there. So for example, there was some nowadays already pretty large trees on the west edge. Also some of the gravels were like growing algae and also getting very dirty, and there's also vegetation growing through. So what we made a plan here and already have implemented it is to make the site look more like this. So we removed the trees and we set up a new large white gravel site there to provide a fourth radiometric brightness at the site. And so this is what the site looked in December. So we had tractors there taking the old stuff away and setting up new gravels in the area. So this is what now it's covered in snow, but in December that's what it looked like. So, but what we have now set up there is that we have 4 different radiometric targets at the site. So there's like the bright white gravel that's about 30-meter circle. So you can basically fit something like up to 10-meter satellite pixel, can get more or less clean pixel there. If you're very strict, maybe just 5-meter pixel, but some 5-meter resolution. Then we have the biggest one is the 40 meters on the gray, and then we have also 2 smaller 14-meter circles on these 2 darker gravels. And then the idea is also that we provide some sort of geometric targets there to evaluate the resolution of the images. So basically these knife edge shapes in here can be used for very high resolution data. You can use the edges here for a slanted edge method, and then the resolution-based methods for up to 5-meter resolution targets in pixels in here. Then we're also considering adding some sort of like concrete slab bar targets here on the edge that would give you even finer resolution for the sites, but that's just planning at this stage. So we have already taken some measurements of the gravel in there. So in this graphs, the relevant is the blue line in here. So basically, we tested different gravels, what we would use for the white gravel there, and found out that basically this dolomite gravel was the best. It has a pretty flat reflectance spectrum. Then we also did some preliminary BRDF calibration, so reflectance anisotropy measurements from those. So basically in here you can see what is the brightness or the reflectance factor of the gravel from different view angles. So if the sun is behind your head and you're looking 10 degrees from nadir, it gets about 5% brighter than looking straight down. And if you look it towards the sun, again, it gets about 5%. And these are something that we definitely need to be if you want to do accurate calibration and validation of the satellites, these are something that we need to have a proper calibration models to fix, but these are about as good as you can get with any large-scale sites. Then in this project we are now also doing this like planning on what sort of permanent instrumentation and permanent calibration data we would be providing. So what we are planning to add there is definitely some sort of radiometric measurement systems. So we are going to be measuring bottom of atmosphere irradiance, some upwelling gradients from these gravels, and possibly also some reflectance measurements. And these we are considering green monitor sensor by Terramonitor company and HyperNet and possibly also others. Then for atmospheric measurements, we definitely will have there an all-sky camera to record the atmospheric conditions, and possibly also an IRNet instrument for atmospheric parameters. Then at our institute we are very active in the drone systems, so we are considering adding there also some sort of automated drone in a box system that could do a regular time series measurements of the site. Then also we definitely will be providing the site with the very high resolution, like centimeter scale, hyperspectral BRDF and 3D mapping of the site surroundings. This allows the like accurate calibration of the upscaling of the point measurements to larger scale. And then we also have a top-notch radiometric laboratories where we will calibrate the gravel and other targets that we have on the site, so that we know exactly their reflectances and BRDFs. And then also part of the same package, this is not actually not necessarily exactly in Sjökulla, but we have the network of FINREF GNSS stations all over Finland. At 10 of these sites there are these SAR reflectors that these will be made available via SAR CalNet service, so that they can be used in calibration of SAR systems. And then also we are considering using some lakes near Sjökulla for thermal calibration targets, but that's also part of just like future planning. So this is basically my last slide. Our next steps will be that next summer these gravel targets will be usable. If you are taking images of the site, they are there. We will perform calibration of these so that we have data available for that, and we will do this like drone mappings and drone calibrations of these site surroundings. We will also perform some sort of pilot cavalcade campaign using the satellite data to test the calibrations and test the site in practical usage. And then we will complete the planning for what sort of features, instrumentation, and service we will be providing in a longer term at the site. After this, we will be hopefully getting a phase 1 and phase 3 projects for this for setting up the actual site for calibration satellite calibration services, and then also running those in a longer term. That's all.
Thank you very much, Juha. Anyone have a question? We have, I think, time for one or two. Okay, let's have it. I'll come to you.
Yeah, thanks for an interesting talk. I was wondering when the surface is, like, do you make sure that the surface is dry when you collect the target spectra, or if you have maybe some input in when it's wet, what would be the effect?
Yes, definitely there is effect if the surface is moist. And that's one of the reasons that we cannot just do that. We do a laboratory calibration and assume that we will need to have some sort of reflected radiance measurements from the gravel happening in real time. So this will be like the validation of what is the actual state of the gravel. And there are like two different modes of operation that we're considering. There's the continuous operation, where we have like a permanent instrumentation taking measurements there, and that data will be available some sort of data portal. But then also there's campaign-based, where if we have like a active calibration campaign for some system, then we can have also additional validation measurements performed in the field in real time.
So no other questions. So I have a comment to you.
Yep.
I think the drone flying question is something where, from a kind of atmospheric point of view, I think there would be a lot of interest in the fact that if we have simultaneous like drone flights when Sentinel-2, for example, flies over, so that we can see there's quite a lot of data where there's some cloud, but you still see something from the bottom. And I think to get that data out, it would be really to have comparative, like lower, let's say, close to the bottom observations from that. So that could be one idea. So maybe you can put it in the bag.
Yeah, thank you.
Yeah, but thank you very much for this. And let's go back then to Sodankylä. Andreas Colliander will tell now a more concrete example of how CalVal is actually done and not just what we have there as opportunities. Go ahead, Andreas.
All right, thank you. Yeah, and my name is Andreas Colliander. I've been with FMI only 4 months, but I've worked on the calibration and validation of satellites for about 2 decades, and especially passive microwave, which I'm focusing on here. And we'll offer some perspectives on how to use those measurements and activities that's been going on in Sodankylä for some time for those calibration. I'm acknowledging my authors who have been working on this site for a long time already, and established it now ready for to be a ESA super site, as Hanna-Kaisa presented earlier. Okay, so I'm going to start a little bit of motivation using microwave radiometry. So 2 aspects that are relevant for the super site here is hydrologic cycle, which is of course something that sustains the life on Earth and provides fresh water for humanity and all living things. And then forests, which are a critical component of the Earth system, providing carbon storage and for human activities, lumber and raw materials, and of course living habitat for countless of species. So with microwave radiometry, we are sensitive to multiple parameters and state variables in hydrologic cycle and forest ecosystems, and I'm highlighting them here. For soil, we can observe its moisture, its freeze state, its temperature. We can observe different parameters from snow. Also, we can parameterize the water fraction and so forth. And then that links to forest ecosystems where hydrologic cycle and carbon cycle is linked together to maintain the forest ecosystem. And there we can observe, in addition to the hydrologic parameters that are relevant there, also vegetation, biomass, water content, and free state of the vegetation and the soil, which regulates then a lot of those activities there. So there are a number of satellites, microwave remote sensing satellites that are measuring Earth's surface, and relevant frequencies here are 1.4 gigahertz, 6 gigahertz, 10 gigahertz, 19 gigahertz, and 36 gigahertz. And here I'm highlighting a couple of those 1.4 gigahertz satellites. On top left is ESA's SMOS mission and NASA's SMAP satellite that have been operating. The SMOS satellite was launched 2010 and SMAP 2015, and those are the more recent ones. The higher frequencies have been observed with multiple satellites like the SSMI series by NASA for a long time, and JAXA has also provided those higher frequencies a little bit more recently, a bit higher resolution since the early 2000s. And then a very significant satellite is going to be launched by ESA around 2030, SIMR, Copernicus Imaging Microwave Radiometer, that will provide all these frequencies from the same platform, which will be providing game-changing observations for multiple applications, not only on land surface, but across the Earth, ocean, and cryosphere, ice sheets, and so forth. So the main challenge is when we validate satellite retrievals, and here focusing on microwave retrievals, is first of all how to match the parameters that we want to retrieve with the models that we have to model the emission that we measure with the satellites. For example, in soil moisture, we know what the soil moisture is, but then we need to translate that to emission through different equations and models, accounting for soil texture, but also then roughness of the earth and or the soil and ground, and how much there is vegetation there, causing uncertainty in the retrieval. Same for example, snow water equivalent, which can be measured at one point definitively with just collecting the snow sample, but then in the measurement you measure certain emission signals and you want to relate to that. A second fundamental problem is the horizontal representation. So we measure these usually the through measurements point-wise, but there's spatial variability, and the remote sensing measurement is by nature a aerial average of some area. In microwave radiometry, they are typically very large footprints, tens of kilometers, if you measure it from the satellite because of the wavelength. In the previous talk, we saw much higher resolution measurements with completely different scale, but here we need to relate the ground measurements to these large footprints, and usually you need multiple measurements to do that in order to be successful, and that requires resources, which is maybe an obstacle. And then finally there is the vertical representation, so we observe these measurements through medium, and we need to represent that, have the measurements to represent the different stages of that medium and different depths. So we just saw Hanna-Kaisa's presentation on the supersite. Some of you saw that, and I just want to highlight. So what I'm talking about here with microwave radiometer suits very well with these focus areas of the supersite. The forest ecosystems and hydrology and snow are exactly the kind of things that we can measure with microwave radiometry, and that has been measured for a long time at this site. And now with this ESA supersite, it can be even more improved and made more relevant. Regarding the instrument suite available at the supersite, there are multiple radiometers already operating for many years, providing high resolution, continuous measurements of these brightness temperatures at multiple frequencies. So we can do focus studies, which I'll talk a little bit more here. So when we do these validations, we want to use multiple measurements, reference measurements from the soil, then the high resolution tower measurements, which are continuous, so we can establish these process level relationships that can be then translated to understanding the satellite measurements, which are not necessarily so temporarily continuous, and also the just mentioned horizontal representation creates uncertainties that we can isolate here in using these tower measurements, especially when conducting campaigns where we deploy people and instruments. We can uncover a lot of different aspects of those retrievals and target certain uncertainties found in the satellite retrievals. So, for example, here we are looking at a canopy with radiometers, but at the same, so one from the top of the tower here in that diagram, and then we have another radiometer at the bottom of the canopy, and so we can observe the canopy separately from the bottom of the canopy. We can make ground measurements, and then we can also observe the ground with the bottom of the canopy measurement so that we don't have the vegetation there in front of us. So we can isolate these different components that the satellite just sees and estimate their effects on satellite measurements and then translate that into better retrievals. So Sodankylä has been doing this for a long time, and this is super critical, and it's pretty rare that there are these complex measurements available. So it's a really unique site. Here is another aspect they've been doing here is having this network of stations. So hopefully you see there the black dots represent the stations, that you have a couple of photos here on the left-hand side. And then there are these footprints of different radiometer satellites that indicate the scale of the measurements and how, we want to have these representation modeled with multiple measurements so that we can track the different soil moisture behavior, for example, in this case, in different types of landscapes within those footprints. So I have a few examples of what has been done with these measurements. Here on the left side is residual analysis using a calibrated model using the Sodankylä measurements, and then forward model residuals computed based on those. So improving soil moisture retrieval, vegetation retrievals, and also snow effect on those SMOS retrievals there. And then on the right side is a exercise where the red dots show you the original retrieval, which is quite scattered, and then when you use the Sodankylä measurements to recalibrate those parameters, you see that you can get much better retrieval if you were using the right parameters. So those kind of things are really important in order to improve your satellite retrieval. So that was done with the SMAP satellite. A couple of other tower experiments here. The left one shows this multi-angle snow experiment where they were showing how snow affects this low frequency brightness temperature. It has a subtle effect, but it's very important to include in the retrievals during winter time. And then on the right is a very important study regarding retrieving freeze-thaw state of soil. This has been widely cited for it's showing all these different phases of freeze-thaw, freezing and thawing that the 1.4 gigahertz radiometers are sensitive to. Another very interesting study here, the multiple frequency radiometer were pointed to look at the tree over the full season and showing its dependency on temperature at all these different frequencies, and also isolating here the canopy and the stem when the radiometers were scanning that tree continuously. Very unique experiment. Another snow experiment where they removed the snow from an area and see the effect of snow on radiometer. There is an animation there, but looks like it didn't start. And then there's on the right there is oh yeah, you can click it from here. Yeah, cool. Yeah, does it start? Oh, okay. All right. All right. And then on the right there is drone measurements made regarding soil freezing. So this is much higher resolution map of brightness temperature now in tens of meters using that drone measurement. Pretty recent results, those. So finally, I'm going to conclude here. So microwave radiometers provide this unique view of coupled soil vegetation and snow processes across seasons, and we need validation sites to improve those retrievals and develop those retrievals, especially for or particularly for future satellites that are continuing this data record. And the Sodankylä super site provides a really unique site with a lot of facilities and resources to do this work in a very precise way and a diverse way of accounting for scales and temporal, spatial scales and temporal scales, and different viewing geometries. And I'm only talking about here on the passive microwave measurements, but actually this applies to a lot of other measurements, to active microwave and these optical measurements and CO2 measurements. So the site is really unique in its diversity. And eventually they'll support more robust global monitoring of these hydrological relevant parameters like soil moisture, vegetation, and snow conditions. So thank you very much.
Thank you very much, Andreas. So, do we have a question in the audience? I'm scanning, but no questions. So I have to come up with one. What do we do with a saltwater pool in Sodankylä?
What do you mean by that?
A saltwater pool, because one of the very few things that we are missing is that how does sea ice go about as a Calwell object, and I think it would be very cool to have it in this far away from the ocean place to also do this measurement. So it was not so much a question of, but it's for the SAR satellites to be also Calwelled. I think one thing that we are missing is a saltwater pool, so we can go swimming there, of course. But thank you very much, Andreas. I think we have a cool site in Sodankylä. But we have still one more presentation to go. And now we go to our southern friends in Estonia. And Martin Menert is going to present to us what they are doing for vegetation, let's say, monitoring in Calwell. The microphone is there. Okay, go ahead.
Hello. Today's presentation is on the possibilities of calibration of the Sentinel and other satellite missions with the on-ground measurement data, and also with the height data measured by planes. For example, in Estonia, regular flights we do have in summer and spring season. At the Estonian Land and Spatial Development Board. Earlier presentation was about vegetation. So actually our plane flight of the Estonian Land and Spatial Development Board of spring, it is meant mainly for the construction and ground measurements, but about the vegetation it is more suited the summer flights, and the period is about 4 years. So actually the statistics, which will I show you later, it is calculated only with the summer flights data. And actually in Estonia also we have some issues with using the land boards data because there are still some institutions who trust more the ground measurements or the statistical methods. But with the plane measurements, you can do more overall statistics. For example, the pixel, if you have used with the Sentinel, is usually 10 or 20 meters, but with the plane of our country, 1 pixel for height measurement is 4 meters. So actually comparable with Sentinel or even better. And actually one of our later presentations today at this room is about some future mission in Estonia, which uses the radar satellite and companion to that to increase the accuracy of height measurements with Sentinel-1. So actually the plane measurements in every country are quite important to give some huge amount of data for statistics and calibration. So our next slide is about some quite usual or needed application for the height data. It is the statistic not very much published before. It is statistics of heights of vegetation throughout our municipalities. We have 79 municipalities in Estonia, and part of these are in this image. So actually, as you see from the second and third column, we have the 4-year periods, as I mentioned earlier, and like the last, we have now have 3 periods, like 20 till 23rd, and before that also 2 4-year periods. And the second column about some municipalities is long, like 8 years. It is because we have missed 1 flight for some mysterious reason in northeastern part of country in summer of 2016. But otherwise, the data is still quite good. Its accuracy is about like half meters, not better. We have also had experiments to try to estimate the growth of forests, but still not succeeded because of the measurement error. So if in future we combine the plane data and the satellite data, we then may get some statistical methods to improve the accuracy of height measurements. And actually, the slide you are currently viewing, it is only computed with the plane data. So actually that may give insight how the satellite data also can be used in future. And very needed statistics are like there is total area of municipality, then is the forest land inside it, and our calculation is mainly done in that part. So actually that is the analyzed area, and so quite good statistics for planning future land activities in every municipality. It is the mean height of vegetation. So actually you can see, like, compared with between different periods of length 4 years, you can see approximately how the vegetation in different municipalities have changed. In some municipalities we have more forest, in other less. And actually you can see that for example, the very first row, it is one municipality in northeastern part of our country, and it is a comparison of about 8 years, but otherwise the the difference of mean height is about 3 meters, so taller than one human, and it is about like change for 8 years, and it is somewhat similar how they modeled the change of sea level height. So actually also we can measure the change of forest level height, forest height level. And actually, yes, as I mentioned, the future satellite possibilities which can improve the data. And our next slide is about the height classes. So our very usual map for many years have been to distinguish different stages of the forest, and usually there are about 6 height classes. These are not very uniform, but these are the interpretation of one our colleague. But otherwise also it is not a precise measurement which is important, but usually in practice in municipalities it is important the belonging of trees to some height class. And actually also the analysis we have done is about every municipality, and you can see also how the distribution between different height classes has changed with 8 years. So actually it is quite useful information for future forestry planning, and also in that sense, yes, the future satellite missions can give some more data about the height distributions. Usually the height distribution is about like population distribution. It is normal to have elements in every class, and it is not very normal situation if some class is not very represented, because it is not very then possible for future. Yes, so that is a little review of our activities, and especially like one very useful application of the Land and Special Development Board in our local municipalities. And also I think the results can be also used in Finland and other countries where we have the height data and possible for measurement and compare with other height measurements. And so thank you for listening.
Thank you, Martin. So, do we have questions for Martin? Otherwise, I can, if you go one back the slides, because I'm wondering why don't your trees grow? Some of these places don't have felling, because of course felling forest is an explanation why the height goes down. But I think also some of those areas where you don't have kind of like significant amounts of trees being felled, the numbers are going down. For example,
actually, yes, I did not mention that I sorted the table. There is not all municipalities, but I sorted, yes, by the change of mean. So actually the most significant changes are the first row, and then like no significant or almost like 10 centimeters is below. But actually I also did the analysis, not the usual mean, but also with median, but qualitatively the results were the same. So actually, yes, it is not about analysis of 1 pixel, but yes, like the municipality as a whole, and yes.
Yeah, well, I was just wondering, in Finland usually trees are growing, and we can see that in our we have this look at doing these kind of things. I have looked at that data, and I think we have quite a clear kind of growing, and then it more is the felling of trees that affects it. And I was just wondering that It could be explanation that you have had a huge drought or something like that that has also kind of diminished the trees. So some of these events could be happening. But hey, we have a coffee break. I think that is useful for everyone in the first day of a presentation. So Martin, thank you again. And others, don't forget, back here after the coffee break, I think I will have a very cool presentation. And then in the afternoon, we have the future EO mission session that I will host again. So be back even then. Ciao.
Thank you. For small announcement from the organizers. So if Juha-Pekka Keränen is here or somebody knows Juha-Pekka Keränen, so we might have found something important belonging to you. So please contact us.
most people have now adjusted to the Finnish culture, taking their personal space, leaving some seats next to one another. So there's still some empty spaces in the front row if somebody wants to come a little bit closer, if that's your preference. But hey, my name is Lukas Raatikainen. Apparently I'm the scientific chair of this event, even if I just held myself as a speaker in this event. But welcome to Lumituuli to hear a couple of things about satellites. You would have not guessed it, I think. But we're going to have, first of all, we're going to have ICEYE telling most likely something about SAR satellites, if I would have to guess. Let's welcome to the stage the Risto Vehmas from ICEYE with a round of applause, please.
Hey, hello, good morning everyone. So my name is Risto, I'm a SAR engineer from ICEYE. So I'm one of those nerds who usually sit in one of the dark, gloomy corners of the office right next door, there in Maarintie 8. So I usually try to avoid talking to people and try to avoid fresh air as much as I can, but today there's something I really want to talk about. So we have launched this new open data program, and I'm gonna show you how to access this data, what it's all about, and show you some cool examples also from the open data catalog. So probably quite a few of you have heard about ICEYE. There was a few mentions at the keynote speeches as well. So it originates from this very place, so Aalto University. So it's nice to be presenting here. So it feels like home almost. So let's see what it's all about. Is this working? Right. Perfect. Yes. So we operate the biggest commercial SAR constellation at the moment. So actually, I'm ashamed to admit this, but I've lost count how many satellites we actually have at the moment working. So there was a launch like a couple of weeks ago, and watching these launches used to be a big thing at the office, but now it's just, who cares, just a few more satellites in the sky. So what we plan to do in this session is describe this new open data program. So we want to make datasets available for everyone who wants to use them, like scientific users, educators, engineers, SAR geeks, whoever is interested to see that what type of SAR data these like small commercial satellites can provide. So very like noble and high-minded goals, of course. So it's of course has nothing to do with the fact that our competitors were making like jabs at us on social media trying to humiliate us. Of course not. Nothing like this. No, but in all seriousness, our competitors also have these programs, open data programs. Like Capella and Umbra are also small satellite providers, and they've had these programs up for a while. And we realized that it's really nice to have like different kind of systems, because ICEYE operates its own kind of systems. I'm gonna talk a bit about our unique capabilities in the next slides. And our competitors have different systems. So every type of all engineers know that all systems include trade-offs. So our competitors have systems that provide certain type of data, and they're good for different kind of use cases. They might even have better quality in some aspects. But of course, ICEYE has also some very unique capabilities that basically make us the world leader at the moment in these small satellite SARs. So from an engineering perspective, it's really interesting to have this data like publicly available. So I encourage everyone to like explore and experiment with the data that you can find there. So it will be available under AWS bucket. So there will be instructions in our product documentation, and also show you some examples how to access the data. And yes, about the licensing. So basically you're free to do whatever you want with the data as long as you attribute ICEYE, so it's CC BY 4. So we encourage this, all kinds of research, algorithm development, anything you can think of to do with the data. So we'll be very interested to see like what kind of applications people can think of. So this first set of data, so here's a map illustrating like the first batch that you can find right there. So we have about 200 of these data sets at the moment. So this is just to get things going. So we plan to update the catalog regularly to include even more and more data. So the initial set just covers like basically all the different imaging modes. I'll say a few words about the imaging modes in the next slide. So to illustrate the different kind of resolution versus area coverage and the different types of data products that we have. available. And also like the global coverage and different kind of scenes that encourages different type of applications. So basically anything you can think about doing with remote sensing data and SAR data. So we should cover most application bases with this initial data set. But I'm also interested to hear if someone has like some very specific use cases that you would like to see in a public data set. I would be very interested to hear your thoughts later on. Yes, so a few words about this imaging mode. So as I mentioned, so ISA has a pretty unique system compared to our competitors in terms of the system design. So we operate something that's called a phased array antenna. So if you combine that with the fact that we have a very small satellite, like less than 100 kilograms, it means that we have a lot of agility, which basically means that we can like maneuver the satellite, like mechanically steer the antenna, as well as electronically steer the antenna with this phased array. So this allows something that's been very like difficult to achieve, even for the the bigger satellite systems. So combining like large area surveillance modes with very high resolution and detailed imagery. So those are usually like contradictory requirements, but this type of combination of these different properties allows us to overcome these challenges a little bit at least. So it's a pretty unique combination that we can achieve. And here's a figure that illustrates basically the different type of imaging mode in terms of area, in terms of resolution. So the biggest and the most largest area mode is the scan, or even scan wide is the new imaging mode that covers like more than 200 kilometers in the range direction, and then it can be even larger than 300 kilometers along track. So it depends on like what type of area of interest you're interested in. But then when we go from the large area modes, from the scan modes to the other extreme, which are the like very high resolution spot modes. So there we have a 5 by 5 kilometer spotlight that we continuously illuminate during the measurement with the satellite. And the finest resolution is like 25 centimeters on the ground at the moment for this standard like ground projected multi-looked image products. I'll talk a bit about those in a minute. And yes, so these imaging modes, so the names of these imaging modes, they're a bit ISA specific. So this is a battle that we engineers lose to our product people. We don't really like these names. So we just care about the numbers and basically the rough strategy. So dwell and spot, these are not like standard names that spot fine, spot precise, I think is the name. So these are just ISA terms, so they're not universal in that sense. But what is important are the numbers there. So the resolution and the scene size is all that an engineer really cares about. So yes, so then a few words about what type of products data products we actually have there in the bucket. So for these SAR purists or SAR nerds who are all about the pristine, like the purest form of the data, then you will be interested in this what's called the single look complex data, which is basically the focused image product that contains both the amplitude and phase information. So this might be a bit weird if you're not into the radar. So what is this? That's called phase. So it's basically just a very precise measure of the distance to each pixel that you can use for many interesting applications. So it's a bit unfortunate that it's called complex. Like the mathematician who basically invented complex numbers hated this term complex because it's just an additional number. So there's nothing complex about this product. And I'll actually talk a bit more about these products because there's kind of a gap in this like a SAR community, a specialized SAR community, and the signal processing community who uses this like full fidelity complex data, and then the more application-oriented people who are like more interested in the derivative products. But in our opinion, there shouldn't be this big gap, and we're trying to actually bridge this gap with some other additional open source tooling. I'll mention at the end of the presentation. And all of these data products that we have there, they will be in like cloud optimized GeoTIFFs, so GeoTIFF formats, and with some additional metadata files. And basically all of these other product names, so this is also something that the radar community is notoriously bad in like naming these different products, like this GRD, CSI, a bit whatever. So there are no like unified standards between different data providers, and it's a bit of a shameful situation, to be honest. But what really matters is that like basically everything you can derive from the SLC data product. So all of these GRDs and videos and CSIs, if you know what you're doing, you can basically derive them from the SLC data. So probably for the scientific users, the SLC will be the most interesting data format. So just a few words about this data products, these additional data products that I can provide, and the agility that I was mentioning. So what we call a dwell mode is actually just a spot mode with a very long illumination. So this is actually something that's made possible because we can mechanically steer the antenna of the satellite when we make the pass. So it means that we can actually illuminate a target for a very, very long time, like 25 seconds is the standard imaging time for the dwell imaging mode. So it actually means that you can obtain some very interesting information. So when you see the target for a long, long time, like 25 seconds, if you divide the measurement into these smaller segments, you can actually see like the temporal dependence of different scatterers in the scene. Or another way to encode this is to think about it in terms of the illumination angle, from which angle you see which target. So you can see a lot of useful information in these long illumination acquisitions. So this is what is called a colorized subaperture image, so CSI. So there we encode the information in color. Like if you see something in different colors, it means that the scattering is coming from dominantly from a different direction. And then another possibility is just to make it as a simple movie. So it's a SAR video. So we just play these different sections of the measurements as a video. And then just to marvel some fabulous ISSR images, of course, we need to show you some examples. So here's the largest area mode, so scan mode. So this is probably most useful for applications where we need to monitor very large areas. So probably the most important use case at the moment is like maritime routes and observing like large sea areas, detecting ships, monitoring movements in key shipping areas. And of course, maybe some environmental applications like monitoring weather patterns over large sea areas as well could be an interesting application. So here's an example from the Panama Canal. So then we have a strip map. So this is an interesting image. Can you guess what we see actually here in this SAR image? So these are actually frozen rivers somewhere in the tundra. This is a cool looking image. So strip map is the next down from the scan mode. So it's about 30 kilometers in one direction and about 80 kilometers in the horizontal direction in this case. Also good for different environmental monitoring applications where you're necessarily not looking for like detailed target information, but monitoring properties of some surface areas, for example. And then we come to the workhorse that's making probably the most money, because most people are interested in this very high resolution, very high detailed images, so spotlight images. So here's spot fine, which is about 50 centimeter resolution on the ground plane. Here's actually also an interesting image. So you see here some mountains, so some typical SAR phenomena, so layover, and then you see some packed ice there on the left, and then some sea ice as well. So there's probably some water and ice there. So this type of data is probably interesting also for many environmental applications. Yeah, and then we come to these cool color images and videos. So this is an example of Venice in this colorized sub-aperture image format. So this way of coding the information into color is really useful for highlighting like man-made objects, because these sharp corners and like flat plate structures create these reflections that are very direction dependent. So you can only see a strong reflection from a certain direction. So this is exactly where this like dividing the measurement into different segments comes into play, and it's very useful. So there you see bright colors, at least like walls and corners of buildings light up nicely in these colorized images. And then you can play the same thing, just same information but displayed in a different way. So you actually play these individual images that you make from the measurement as a video. So SAR movie night. Another nice video. So here's actually a puzzle for you to think about. So we're operating at microwaves, so SAR is supposed to see through clouds, through fog, through smoke, but there's something interesting going on here. Seems to be something like foggy here. So I will leave this to you as a puzzle to figure out and publish something. What do you see here? And then more color images. So a train station, train tracks, building roofs. Yeah, here's actually a cool example from a mine. So a mine looks quite interesting in a SAR image, because in SAR image, you probably know about these geometric distortions that you see, because we measure the distance to the radar, so we're not actually... So compared to optical, like the projection is different, so the geometrical effects are very interesting in this case. And then more color images, so there you see the power lines, nicely highlighted. It's not a rainbow, it's a power line. And then just one example image from this highest resolution mode, so from the Rotterdam board, just to illustrate that what kind of level of detail you can see in the images. Yes, so I promised to say a few words about these data formats and this gap between the high-end users. No, that's the wrong word. We're not high-end users, we're just geeks. So we use this SLC data, but so the gap I was talking about is mostly about the tooling to use this data. So there's a lot of open source tooling to exploit optical imagery and this type of imagery. But for SAR, it's still pretty niche. So it's mostly these like big defense and military users that only use this like full resolution complex data. So what we're planning to do is actually release some open source tooling that you can use this SLC data format that we have. So there's this open source software called QGIS you can use for GeoTIFF files to view them, and it's easy to introduce like your own Python plugins. And we're planning to release actually one Python plugin that then just hopefully encourages people to even develop more on top of that, more type of applications and tooling, how to actually use this data. And this initial release include only these like single data sets. So what we also plan to do in the future is to include like coherent stacks. So what does that mean? That means that we obtain images from the same locations at different times with the same kind of viewing geometry. And then we can compare these, like the phase information in the images, to do something that's called interferometric SAR processing. And that basically means that you can obtain very fine detailed information about the changes that happen in the scene. So here's one cool example, one feel-good story for the end. So there's actually a marriage proposal written in this field. And you can only see it if you compare like two different SAR acquisitions and the phase and what's happened there. So if you look at an optical image or just a single SAR image, you cannot actually see what's written there in the field. And there, if you want to read the full story, there's a link there. And as I mentioned, all of this information will be available. All the links to the data program will be in our product documentation. So there's a link to this Stack browser interface where you can actually download all the products and browse the catalog. And there's also a link for the initial images. All right, that's all for today. And yes, I would be very interested to hear if there's some like scientific users and people who are interested in applications. Like what type of data would you be interested to see in this open data program?
Excellent stuff, I would say. It's always great to see a Finnish company doing such a progressive work and actually now expanding the data for everybody to use and innovate new kind of things. Huge salute to you guys for doing that. Do we have any questions in the crowd? Oh, okay, already a couple hands going up, 3 hands going up. Let's start from there, that side of the room. Let's get the question started.
Hi. I have a question about the small gift where you explain the 2 different modes, the spot and drain mode, I think, I don't remember. I'm a bit confused by the color code you used for the so do you measure, like, can you measure some Doppler shift, or is just like a color code to represent different, let's say, snapshots?
Yes, okay, that's a good question and a good point to clarify. So the color coding is just to, basically, you can make a SAR image from a small part of the measurement of the same scene. And that is just a normal grayscale image. But then you can combine these different grayscale images. So basically have different weights for each of the images and make the red, green, and blue bands of the image by combining these different amplitude images. So that's what the color coding is in this case.
Okay, thanks.
Borderline magic, I would say. There was one question from there.
Thank you. Timo Pyhalahti from Syke. Very inspiring. I was just wondering if these example of images you are publishing, are they just examples of the different kind of terrains, or are there also some kind of events like a breakup of ice on rivers or something like that included? And if there's any in situ data available for training with these tests? Thank you.
So at the moment, probably the datasets I was showing, we don't have this kind of in situ information. And probably, I'm not aware if we had any of these interesting events going on. But that's something we probably would like to do in the future more as we expand the datasets. Yes, definitely.
Good. Then next question over here. And then over there.
Hi, so I actually have two kind of separate questions. For the publications that you are going to release, do you have any estimates for the release dates, or do you have a time period for those, for the plugins and for the datasets?
So do you mean the datasets, more datasets? Or?
The datasets and for the plugin that you mentioned as well.
Right. So the plugin we plan to release probably Q2 this year, so before summer, I would say. I would hope so. And the datasets, so that's, I think that will be up to what kind of ideas we get and what were we interested to do. So that's why I would be interested to hear your ideas as well for the additional datasets.
And then the other question was that now that you are showing this image, and when you have the SAR videos, do you have examples of the use cases of applications for those SAR videos where they are applied at the moment?
Right. So probably one of the most common use cases is just to highlight movement in the scene. So what is changing during a single measurement, because it's like 25 to 30 seconds. It's quite a long time, so you can probably see some bright targets are moving in the scene. You can probably indicate those. That's one example. And then also those examples where you saw the sea state fluctuating quite heavily, so you can actually derive some parameters about the weather from those videos.
Okay, thank you.
And next question over there.
Hi, just a question about the ground track repeat orbits. Are you planning to collect more data over using the same orbital parameters so that you can do INSAR coherent change detection over areas that would be of high interest, for example, in eastern Ukraine that might experience lots of building damage and infrastructure damage?
Yes, so the ground track repeat orbits, so that's like the big vision that the company wants to have. We want to have more and more satellites on these orbits that can be used to monitor these certain areas with one-day repeat, the exact same geometry. And we do have some interesting data sets, but we didn't include them in this initial release. We definitely want to increase more and more of those as well in the future. So yes, that's definitely a direction we're going into.
Good. Any further questions from the crowd at this point? I don't see any hands raising up, but I guess you can still go Pakristo later on about these topics. You have a stand here, if I remember correctly.
Right, yes. So we have stand, I think it's upstairs in the C section, so please come pester us there as well if you are interested to hear more.
Thank you once again, and one round of applause for this presentation. Thank you. Excellent. Next up, we have a keynote. We're going to still be in the satellite orbit, if I would have to make a joke about this topic. But this time from Sweden, we have Adam Dubroe from Swedish Meteorological and Hydrological Institute telling stuff about satellites, if I would have to guess. But let's welcome him to the stage with a huge round of applause. Thank you.
Thank you very much. Thank you very much for having me and inviting me to this conference. I'm really thrilled. I'm going to look forward to the coming days. Yeah, I had a little bit, since it's my first time here at this conference, so I was not sure quite about the audience. It might be a bit varied from industry and meteorology, atmospheric science, Earth observations. So hopefully it will be interesting for all of you, some of it. Arctic Weather Satellite, AWS, that's something different from a cloud service provider. This is a satellite instrument to measure clouds and humidity and temperature. I will focus on of course, the support to weather forecasting, and the focus is the Nordic region, but I will actually also go into the global. And I thank my co-authors at SMHI and Met Norway, and also many other colleagues at the European Centre in Reading, Meteo France, DMI, FMI, Chalmers, and the Danish Technical University. And also ESA for sponsoring this project that part of the talk is based on. So just a little recap. AWS, the Arctic Weather Satellite, was conceived at a ministerial ESA meeting in 2019, and it kicked off in 2021. It was launched 3 years after from California on a beautiful day, August 16, or more than 1.5 years ago. It's not a CubeSat, it's a small satellite. It's actually, you see it on the next page here, being released from the Transporter 11 launcher. It's like a dishwasher-sized satellite with one instrument. And it's a new space concept, so it's kind of a little bit new for ESA to do this kind of rapid development. And I mean, within 3 years, you build a satellite and launch it. And it's you can say the precursor, prototype for a constellation of AWS satellites that I will talk a little bit more about later. So here it is, an artistic view of the Arctic weather satellite, and it's a big European collaboration, actually. Also Nordic collaboration. The Nordic countries is covering more than half of the budget of 42 million euro, with Sweden in the lead, but also Finland, Norway, Denmark has contributed significantly, and also industry in Norway, Denmark, Finland is participating, among many other companies in Europe. But the main contractor for the platform is OSP Sweden in Kista, north of Stockholm, and Omnisys Instruments on the west coast for the instrument. So here's just a beautiful view of the Earth from one of the eyes of the Arctic Weather Satellite, April last year, mainly sensitive to atmospheric humidity. Okay, so AWS is also, of course, building on experience so far. So it's both taking care of heritage sensors in this kind of region, but it also has some innovation. So let's start with the innovation. So normally weather satellites, they measure in the infrared and visible, or the microwave. So in the infrared visible, you are about sensitive to micrometer particles, like small ice particles, cloud ice, liquid water droplets in clouds, which is very good because you can, that's what we want to measure. We want to measure clouds. for weather forecasting. And on the microwave scale, you are sensitive to heavy precipitation, graupull, big particles. But so far we haven't actually, I mean, you have these kind of sensors, you have many sensors in the infrared visible, you have the geostationary satellites, the new Meteosat, for instance, FCI, you have MODIS, which is measuring in this region, you have many satellites, weather satellites. You also have very many satellites and sensors measuring in the microwave. You have the AMSU, MHS, ATMS, many weather crucial platforms. And here we list MWI, which is a coming European sensor on the EPS second generation, and the ICI, Ice Cloud Imager, which go into the sub-millimeter region. But actually AWS was the first to go into the sub-millimeter region to measure this, to bridging the gap between the microwave and the infrared, which is really nice. So here you see just an example of a storm for 1 year ago off the coast of Mozambique, seen by FCI, the Meteosat geostationary satellite instrument in measuring the visible and infrared on the left. And what you see is the instrument is very sensitive to small particles, so it doesn't really penetrate the cloud system. Do you, on the other hand, go to the microwave, like the 50 gigahertz and the 89 gigahertz in the middle column, you see that at the 50 gigahertz, the cloud is almost transparent. So you look all the way to the ground. It is sensitive to oxygen in the atmosphere and can thereby deduct something about the temperature, vertical temperature structure. But do you go up in frequency and down in wavelengths towards the millimeter, sub-millimeter region in the 165, you start to see more. And when you go to the 325, the real sub-millimeter channels, which is the innovation of AWS, you actually start to see something which a little bit look like the infrared. So you see how it actually nicely bridging the gap. Here's just an overview of the radiometer. It has 19 spectral channels in the microwave region from 50 to 330 gigahertz. And as I said, it's sensitive to humidity and temperature in the atmosphere. The different channels are situated around absorption lines due to oxygen and water vapor. And by putting the channels a bit away from the absorption line, you can penetrate deeper into the atmosphere. And that's what these curves are showing, that the channels are sensitive to different parts of the atmosphere due to temperature and humidity. There are many things you can say about AWS. One thing which is a little bit peculiar and also a nice example of a trade-off for a new space concept is that the 4 feed horns on board covering the 19 channels, they actually have completely different geolocation views. So one measurement at the same time will be quite different on Earth. They will be tens and even 100 kilometers apart. But since the satellite is moving fast, I mean, the same spot will be measured soon after. So no problem, because weather doesn't go that fast. It's within a few milliseconds. So here you see an example of the difference. And that is because you have one mirror on board. And then you have 4 feed horns that point into this mirror, and then you simply by geometry you spread the geolocation on ground. The satellite is synchronous polar orbit. It's in about 600 kilometers, so it's lower than the heritage big satellites that we're used to in the weather service. It has a local ascending node of 22:35, so 10:30 in the evening. And to the right you see how it it complements a bit the big systems. The JPSS is the American system. That's a big platform of 4,000 kilograms, so 4 tons. The same is the METOP BC satellites. They're also very big satellites with many instruments, very expensive. So these are the backbone systems that we are used to. Then we also have the Chinese that also fills the early morning. But you see here AWS is filling a gap in the time, but we'll come back to that with EPS Sterna later. It also has, which is very nice for regional weather forecasting and short-term forecasting. We want the data fast, so it has direct broadcast on board, sending the data to ground while it observes. And that here I show an example of, I think it's mostly received from Sodankylä here in this mosaic of 4 consecutive passes seen by a ground station in the Nordic region. So then you will have data within minutes after observation. So I will show some early evaluation results, some examples. I cannot cover everything, of course. So concerning geolocation, I showed you this special scanning of AWS with the 4 different feed horns. In each feed horn, at least the 3 first feed horns, you have window channels that are not that sensitive to atmospheric humidity or oxygen. And there you can actually get landmarks, and by geolocation, by matching with landmarks, you can say something about your geolocation accuracy. And the bottom line is here that we are within kilometers, and the footprints are several kilometers. So it's a fraction of a footprint, the geolocation accuracy, which is nice. So it's within the specification. We have also in the Nordic countries done an evaluation and a preparation to use the data in a regional weather forecasting model. That is what we call NWP, numerical weather prediction. In this case, it's the Harmony Aurora model. It's a 2.5 kilometer horizontal resolution. We use what is called 3D variational assimilation. And 3-hour cycling, that means that every 3 hours there will be issued an analysis and a forecast. And we run on these 2 domains. Currently we are running now in what is called passive mode. That means that the data are monitored in the Arctic region since November. And well, you can see more on this web page on what we have been doing in this project. Just some very early monitoring of the channels. It may be a little bit difficult to see from the back row here, but in NWP it offers a really nice framework to in an objective way look at observations of different observation systems and see how they are consistent with the model's view of the atmosphere. And then that is a common tool to look at the so-called background state. So how the model sees the atmosphere, and then the observation. And then you compare the observations over time, and you can do standard deviations and in this case bias, to look at the bias of the channels over time. And what we want to see is that they are stable in time. We also want them to be as small as possible. And 2 nice things here in the very early part of operations of AWS. This is from January 2025, before it became operational. It became operational in June. So just 2 take-home messages here. It's stable over time, and also when we got an updated, much better side lobe correction software in the ground segment, then it actually went down the bias. So that's the jump you see in mid-March. And then we can go on monitoring the channels after this period, and that's what we are doing. Here, another example of the another aspect of the AWS. There is a heavy oversampling, so the temperature channels are are really, they have a very short integration time. So to actually get down the noise, you would need to average several footprints. And that's what we're doing with this 3x3 averaging. And this is just to confirm that when we do the averaging, the blue line gets closer to the red line. The red line is another instrument, a heritage instrument, MetOpC, so one of these big expensive systems that we want to be as good as. And we can conclude that we are in the same ballpark as these systems. I have to say that there has been many attempts to assimilate, bring in these new space satellites in numerical weather prediction from other actors like Spire and others. But these kind of microwave observations, it's the first time that they actually go in operational weather prediction, because they are proven to be good enough. And I mean, there is quite a threshold to get the data in and make an impact, because we already have many good observation systems. Just one overview to calm you that it looks like AWS is bringing mostly blue, good data with it from our colleagues at Météo France. So they run a global model, and this is looking at the short to mid-range weather forecasts, and that is a typical thing you do in this NWP community, to see whether when you bring in a new data source, how does it perform against different other observation types. And then on the x-axis you have the time scale on how long the forecast is, and on the y-axis you have the vertical atmosphere. So mostly it's actually bringing positive impact. Here another one from our colleagues at the European Center for Medium Range Weather Forecasting, looking at also these backbone systems, comparing AWS to these backbone systems. And the x-axis here is a way to measure how impactful the data is on the improving the weather forecast. And very nicely you see AWS both concerning humidity and temperature is on the same page as these much more expensive, bigger platforms. So I hope I have a little time to go into the future. So as I said, it is a precursor to a constellation, and that's the whole point of it, that we have, I mean, the space industry, ESA and partners have shown that it's possible to build a cheap satellite, well, cheap, relatively, in a fast pace, and that makes it possible to actually afford to have a constellation of many such satellites. So it's like 1% of the cost of AWS is like 1% of the big systems. So that means you can actually have many of these. So here just an example of looking at simulated data. If you try to the lower left corner here, you can imagine yourself standing in the middle of Italy and say, how long does I have to wait until I get coverage from this kind of satellite? If you have 6 AWS satellites plus the backbone systems, then you will have to wait like at most 1 hour, a little bit more than 1 hour, but generally less than 30 minutes. Now you see some dips, you see some jumps there where you have a little longer time, compared to if you didn't have the EPS Sterna constellation, then you would actually have 3 times a day you will have a long wait until you get coverage. So frequent AWS data opens up for kind of different kind of applications of probably a lot of AI driven, data-driven forecasting you could do with these kind of data. We want to use more of the EPS Sterna in the new numerical weather prediction models. But you can also imagine you can do kind of data-driven nowcasting. Here's an example of what we do at SMHI in the framework of the EUMETSAT nowcasting SAF, it's called, where we have trained a neural network with the surface-based Baltrad radar data, active microwave data, against another kind of passive microwave sensor, and then applied it to AWS. So this is, I think, a little bit look into the future, or actually very near future. We already have something like this at SMHI, where we do analysis, and the next step is to do forecasting. So I will finish here, and I hope there will be a few questions. I just have 3 summary slides, boring bullets, but more or less saying what I've already said. Yeah, the first Swedish-built weather satellite, we call it Swedish, but it is Nordic European, but Sweden has a big part in it. It was operational June 5th last year, and now ESA and EUMETSAT has actually secured operations until the end of 2029. Of course, if it's all is well with AWS, the Arctic Weather Satellite, I don't see any obstacles for actually funding it further, but you have to go back to the member states and ask if they will spend more money on it. So a little bit more nerdy and NWP language here. We have looked at the biases and standard deviation noise, and they are stable over time, and they are comparable to other microwave sounders. What I didn't talk so much about here, there are many things you could talk about. There are some peculiarities also in the data. There are some quite strong scan dependency in the bias of the humidity channels, but it can actually be handled with within the NWP framework. And the first preliminary trial experiments showed very promising impact on short and mid-range forecasts. The European Centre started operationally using the data last summer. We are about to start. We started, as I said, in November in the operations on the Arctic, Arctic, but it hasn't been turned on to actually provide impact yet. They need to follow it for a couple of months, my colleagues in Norway, before they can safely put it on. And then finally, we got approval of this big program, the EPS Sterna constellation, which is very nice. 6 satellites in 3 different orbital planes, complementing the backbone systems, and delivering these kind of data until 1942, with 20 satellites constantly being replenished. So yeah, thank you, that's all.
Thank you, Adam, for this presentation. We have time for a couple of questions, if there is any questions in the crowd. If any questions, please raise your hand and we'll pick the microphone for you. While you're still wondering questions, I have actually one question for you. You already talked about the near future, what's going to happen in this scene, let's put it this way. What do you think is going to happen, or what do you wish would happen in the satellite monitoring of weather in the long term? Let's put it in the next 30 years. What would be your, what would you wish to see? Let's put it this way. Your dreams come true.
I'm not prepared for this question, but it's a hard question. But I think it would be very nice to see continued international collaboration. And in these times, I would wish that you would get closer and closer between commercial sector and governmental sector and across borders. I think we have a very good history in meteorology to work well on a global scale. We are doing it, at least until now, between agencies on different sides of the Atlantic and with China, India, and so on. So my fear is that you will get, that each
part of the world would close itself, and that would be disastrous. So I really hope that we can continue with sharing data openly and collaborate both between commercial sector, governmental sector, and across the world. Yeah.
Let's hope that the collaboration works and extends in the long term. No question as of now, if I'm not mistaken. So thank you for the presentation. There's one. Microphone over there, please. No hurry.
I wonder if the collaboration with optical satellite imagery has been explored. Can this actually bring some information for the clear atmosphere for correcting for the optical measurements?
I mean, optical and infrared are already used in weather forecasting, not to the extent that it could, I would say. I'm not sure whether that's what you are hitting at.
To specify more, to correct for the optical images of the terrain and sea areas and so on, so to improve the detection accuracy with multispectral and hyperspectral satellite images because of the atmospheric correction procedures.
I mean, you could use the, I mean, as I said, the NWP is a fantastic framework because it has so many observation types in this blended in. So it's the kind of the best guess of the atmospheric state that we have today. But I mean, today, I mean, we are living in a disruptive world also in the scientific development. I mean, and I'm not sure how it will look even in 5 years with numerical weather prediction models, because there are these data-driven initiatives are really showing that they are very capable and bringing in all kinds of observations in a big spaghetti, and letting the AI systems predict the future state of the atmosphere. So. But I think that was not really an answer to the question. But microwaves are very different from optical, and here we are working with very big footprints. So I'm not sure. Yeah.
Tough question. Yeah. Okay. Thank you everybody for attending, and thank you for presenting, Adam and Risto, both of you. One more round of applause for this presentation. Thank you. Next up, based on the schedule, we're actually going to have the general keynotes in the Kaleva, in the big hall, starting 11:50, so in about 12 minutes. You have time to get some coffee and maybe go to the bathroom before that. So please join us at the Kaleva, the big room. There should be some good stuff coming up, so we'll see you there in a couple of minutes. And gracias.
So now I'm speaking here while the Windows audio is playing. Do we have any Do we have any problem up there? This is the microphone and audio both at the same time. Very nice.
Yeah, so with the microphone, just tip. The usual is a so-called like thumb length. So it's around this far. And then, so it doesn't like, like all the breathing and when you speak, then you just tilt it like here. And this is like very well. Now I can speak and it sounds very well, and then it will go to the stream very fine. Because otherwise the problem will be that it's then, if I start to get like, I would say, it's not a laser, but it's usually with the peer that it slowly goes down here, and then you can't almost anymore here. Okay. So that's why this is like, well, yeah.
So you said that like thumb rule, like you can speak like this,
far.
yeah?
Yeah, that's far, and then usually tilt a bit.
Okay,
yeah.
so yeah.
Like here, around the chin, yeah, like that. Yeah.
Yeah, okay.
Yeah, like that. Yeah, that's.
Yeah, so this is good. You can hear me now.
Yeah.
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 Good.
Yeah.
Yeah, this is all. Is it working? Yeah, great. We have sound. Yes, yes. So welcome everybody to this hyperspectral Earth observation session. My name is Anu-Maija Sundström. I work at the Finnish Meteorological Institute, and I will be chairing this session. And at this session, so we have some changes in the program. So we will have 4 talks. So actually the 4th talk in the program today is unfortunately cancelled. So we will have at the end of the session a little bit change of the program. But without further ado, so I will give floor to Jarden Mistein, who is talking about advancing land cover analysis, and she is from Kuvaspace.
Is the microphone working? Yeah. Hello, everyone. Thank you for attending my session. I'm Jarden from Kuvaspace, and I'm excited to be here. It's a kind of a full circle moment for me. Last year, I started my journey with Kuva at this conference, so now I get to show you what I've been doing in the years since. I'll be talking about advancing land cover analysis through hyperfield constellation interoperability. It's a big name, but I will break it down for you, don't worry. So what I'll be talking about, first of all, what is land cover analysis? Why do we care about it and the current challenges and systems that we have? Then I will have an introduction to Kuva Space and our hyperfield constellation. I'll be talking about hyperfield's data interoperability, which is how we work together with other systems to solve the problems. And then we will have the conclusions. So let's start with current challenges in land cover analysis. What is land cover analysis? If you look at the image on the right, it's a very colorful image of Espoo and Helsinki, taken from ESA World Cover. What we see in the different colors is different land cover classes. If you see in green, we have tree cover. Red is the built-up or man-made material, which is most of the city. The blue is the permanent water bodies. And we have this map globally for the whole planet. And why do we want to use it? This kind of map, they dictate policies in the EU or for other countries, if it's in agriculture, sustainability, if it's urban planning, you can use it for a lot of different applications, and they're very important. How do we produce these maps? We have different European systems currently in space. If we're talking about Sentinel-2, Prisma, the future CHIME mission, very high resolution imagery satellites. Every system has its own limitations. The most prominent one is revisit times. If you only have one satellite or two satellites in space, your revisit time is going to be once a week, once a month. And what is the problem? These maps change all the time. Just think that you're relying on environmental data or land classes from a year ago, like they're probably changed already. You're relying on outdated information. And these maps, they take a lot of data to produce, so they're normally published every 6 to 10 years. If we look at the ESA map, currently it's from 2021. Just think about the changes since then. And another problem, if you're a company that is creating an AI model for this land cover analysis, you're also relying on outdated model, on outdated data, so your model is going to give outdated results and insights. This is where we come in, Kuva Space. So a little bit about Kuva Space, if you haven't met us already. We are a Finnish-based company. We're about to celebrate our 10-year anniversary this year. We are building in-house hyperspectral satellites, and we also analyze the data, and we build in-house deep learning models. So we do everything from beginning to the end, from building the satellites to giving you the insights. Currently, we have 2 satellites in orbit from our first generation, and by 2030, we want our constellation to have around 100 satellites, which will give you insights in 10 minutes, since it was pictured in space. So why do we use hyperspectral in these specific cases of land cover? With hyperspectral, we're able to identify different materials, reveal invisible materials or camouflage, and detect changes that might not be detectable if you're just using optical sensors or even radar or optical and multispectral. They each have their own advantages. Hyperspectral is specifically for detecting the different materials. This is the design of our constellation. On the left, we have Hyperfield 1, currently 2 satellites in orbit. On the right, we have the new design that we're already launching at the end of this year, Hyperfield 2. And here is some dry parameters. I won't be going over everything, we don't have time. But the main thing is that currently we are in the VIS and the near range. And with our next generation satellite, we're going to go into the SWIR, so deeper into the infrared, and also have very high resolution camera on board. Now, why do we want to launch so many satellites? If you look at the revisit time, when we're going to have our full constellation, it's going to give you 5 daily revisits. If you're looking at high altitudes, or between 2 and 3 daily revisits of the same place at lower altitudes. And if you compare it to the other systems, which only visit every few days, you can really tell the difference. Let's say that you only image once a week, and it's very reliant on the weather. If you get bad weather, now you have 2 weeks gap in your data. So it's very important to constantly be getting new data. So let's talk about the data interoperability. How do we work with these other systems or complement them with our constellation? First of all, we have to make sure that the quality of our data and the formats are the same that you are used to with other scientific grade missions. If you're using Sentinel data, we want to make sure that when you work with our data, you can just plug it in the same way that you're used to Sentinel, same names, same data processing level, same format. And we're part of the Copernicus program, so we have to make sure that we keep the same data quality level that is expected from these scientific missions. If it's radiometric accuracy or geometric accuracy. Here you have an example of our georeferencing algorithms put on the Google Maps and compared to Sentinel. You can see that the pixels match exactly. Just think about it, if you are 1 pixel off, you're sampling spectra of another material, so it's very important to be very precise. Here is some radiometric accuracy, data quality, performance check that we're doing. On the left, you have comparison. On the x-axis, you have hyperfield reflectance. On the y-axis, you have Sentinel-2. We want to make sure that we get 1-to-1 on the spectra. On the right is a comparison to LaCroix site, which is a RadCalNet site, so ground calibration site. So we keep improving our calibration. We make sure all the time that we're up to the standards that are expected from us. Now, the deep learning model that we're developing for generating these land cover maps, it starts by acquiring global images that have the same overpass with Sentinel-2. Then we train our model with the labels from the ESA world cover map. Once we validate the model against unseen images and we are happy with the accuracy, then we can go ahead and process our entire data archive. Currently we have 25,000 images. By that time, the model has already learned to identify the different classes by their spectral signature. And then when we're constantly gathering new data, we're able to constantly update the map. Not once every 6 years. Every time the satellite goes over, we can keep updating the map. Okay, so here are some results from our model. If you look in the table, you can see that the accuracy of hyperfield 1A is good. It's not as good as Sentinel-2. When we used the fused model, it improved the accuracy of Sentinel-2. But something very important that we noticed. If you look at the raw data, it looks like hyperfield is not doing as good of a job as Sentinel-2. But if you actually look at the labels that our model predicted and compare it to the Sentinel and the ground truth, it seems like Sentinel matches the ground truth pretty well. Hyperfield, for some reason, detected some green areas. If you compare it to the actual high-resolution image, the optical image, you can see that Hyperfield was able to detect some classes that obviously, if you look with your eyes, you can see that they are there, but the world cover map is not updated with this information. So it just shows you again, you can have the best model. If it's trained with the wrong data, it's going to tell you that your accuracy is great, but if you compare it to real life, it might not actually be the truth. So it's very important to keep these models up to date, not only once every 6 years. Okay, so how is Hyperfield acting as a solution? When we have the 100 satellites, we can constantly keep acquiring new data and updating our maps. We're going to have onboard processing, which will give us near real-time updates and give the users near real-time updates. in our new design, we're going to have on board SWIR camera and very high resolution camera. So just like in the slide before, where you were able to see with your eyes if the land cover model is true or not, if we have the very high resolution camera on board, it will give us very easy verification to our model. We won't have to rely on third parties. And of course, we're going to gather on a global scale many more images. It will help us to validate our model, make it more accessible to different regions. And we also have a plan to integrate Sentinel-1, which is using SAR to improve our model and test if it actually improves the precision of our model. Okay, so let's conclude this session. We have seen that if you're using outdated land cover maps, you will get outdated insights, which is the most important thing. We have seen that if you combine hyperfield with Sentinel, you get an improved model, improved accuracy, and improved precision. And when we have the 100 satellites in space, we can generate this near real-time land cover image and be the solution to the challenges that we've seen before in the constantly changing environment. And it's always important to keep up with the data quality standards. So it's important that we follow that and we keep correcting ourselves and making sure that everything is as high data quality as possible. And that was my presentation. You're welcome to come visit us at our booth upstairs if you have more questions or you want to ask more about the satellite, about the data. Yeah, thank you.
Thank you. Thank you, very impressive images and work. So do we have questions?
Hey, thanks for the presentation. About the VHR camera that you are adding, is it just about the verification of your product, or are you actually planning to also start selling the VHR imagery?
So we don't only do land cover with our satellites. This is just one example. It's going to have a lot of uses. So it's not only for verification. We need it for other models, and it's always good to have very high resolution camera. You can infuse it with your models and get better results. But we don't plan on selling the very high resolution photos just by themselves as a product.
Okay, is there a question? Yeah.
Thanks. Could you talk a little bit about the camouflaging and decoy line of work, and is that on an automated basis, or is that done manually?
Sorry,
Is it done automated or on a manual basis?
The camouflage?
And yeah, decoy detection.
Yeah, all of our insights will be based on deep learning models. So the idea is that if you're a client that's interested in that application, our team is building that specific model, which automatically recognize camouflage materials or detect anomalies in an area. So if you see a forest, which is forestry, and then you see something man-made material in it, it's supposed to pop up an alert and let you know.
Okay, thank you. So let's give applause once more. And yeah.
Thank you.
And we will move to the next presentation, which is given by Susanna Karlqvist from Aalto University, and it's about the surface moisture of northern peatlands. Do we call it? There is a little bit technical advice needed here downstairs. Could you technique in the upstairs. Could you visit here for a while? Yeah.
Sorry, I'm just putting my own timer so I don't go too much overboard. So, hi, I'm Susanna, a doctoral student from Aalto University, and I'm here to talk about my research on estimating surface moisture content of northern peatlands from hyper and multispectral satellite data. Okay. So, why do we want to study peatland moisture? Well, peatlands are a very important part of the global carbon cycle, as although they cover only less than 4% of the Earth's landmass, they store about 30% of the world's organic soil carbon, making peatlands the biggest terrestrial carbon storage. And the peatland health and ability to store this carbon is highly sensitive to moisture conditions, as peat formation happens in waterlogged conditions. Therefore, by monitoring moisture content, we can evaluate peatland health, identify vulnerable areas, and also evaluate restoration efforts of those already degraded sites. With satellite remote sensing, we can monitor large areas. However, existing satellite-derived soil moisture products often perform quite poorly in peatlands, have quite coarse spatial resolution, which doesn't really capture the network of peatlands that we have. Therefore, in this study, I test different hyperspectral methods to estimate peatland surface moisture, and I compare these against more traditional multispectral methods. Okay, continue. Yes, for this study, we had data from 9 different peatland sites from Finland, Sweden, and Estonia, covering a quite large spatial gradient. And we had reference surface data from all of these sites. From 3 sites, the surface data was collected manually, and from all the other sites, the reference data was collected with automatic data loggers. Therefore, we were able to use the exact moisture from the time of the satellite image acquisition. From those sites that we had manual measurements, the moisture was collected maximum 7 days from the actual moisture measurement, but we did also evaluate the weather conditions to see if there was a lot of precipitation or other weather events that might have affected the moisture. From all the sites, we had both hyperspectral Nmap and multispectral Sentinel-2 data. So here when I say 1 images, I mean that there was 1 Nmap image and a corresponding Sentinel-2 image from the same time period. And in fact, all corresponding images were either from the same day or 1 day apart, except in 2 instances where there was few days between the Nmap and Sentinel-2 images, but these sites had automatic loggers, so we were still able to get the actual moisture from the satellite image acquisition. Here we have the reference spectra, means spectra for all the sites and also all the individual spectra, both for Nmap and Sentinel-2. The Sentinel-2 data has a 30-meter spatial resolution, and we use 206 bands. Those of you familiar with Nmap data, you might notice that we are only using bands in the overlapping region where both Nmap's visual near-infrared sensor and shortwave infrared sensor collect data. So in that region, we are only using the visual near-infrared bands. And then with multispectral data, we use 10 bands, those that had 10-meter or 20-meter resolution. And for the methods, for the hyperspectral Nmap data, we tested 5 different methods, 3 of which were more traditional spectral moisture indices, the normalized difference water index, sphere transformed reflectance, and the water index. Then the other 2 methods were a full spectrum analysis and continuous wavelet transform. And this full spectrum analysis means that we used all Nmap bands in our kernel partial least square model as predictors, and the continuous wavelet transform used all the CVT coefficients as predictors. With Sentinel-2 data, we used 2 moisture indices, NDWI and STR, as well as all the Sentinel-2 bands as predictors. We use kernel partial least squares as our regression model because PLS models are useful when working with highly collinear data and when the number of predictors exceeds the number of observations, both of which was true for our data with Nmap bands and continuous wavelet transform. And with kernel partial least squares, we were also able to capture possible nonlinear relationships. And for the kernel, we used Gaussian kernel. Yeah. And for the results, all the tested moisture indices performed poorly. And here I'm only showing the best moisture indices for both hyper and multispectral data. So as we can see, they don't really predict low moisture values or actually too high moisture values either. In contrast, the other 3 models worked quite nicely. The continuous wavelet transformed coefficients outperformed the other 2 models, and the Nmap bands also were quite much better than the Sentinel-2 band model, even though the Sentinel-2 band had better spatial resolution. So these results indicate that the spectral resolution is actually more significant for peatland moisture estimation than the spatial resolution. And so as you can see, the continuous wavelet transform was the best performing model, and this can be attributed to its ability to decompose spectral signatures into multiscale representation. And so what actually is continuous wavelet transform? It is a signal processing technique that converts signals into a different form by scaling and shifting a matter wavelet. The scaling factor controls the width of the matter wavelet, and the shifting factor moves it along the spectral range. In our study, we used a real-valued Morlet wavelet as the motor wavelet, and we applied 9 different scales from 2 to 32. Here is an illustration how the Morlet wavelet looks like at all of these different scales. So the smaller the scale, less adjacent bands will affect the CVT coefficients, but as the scale gets larger, more bands are affected at the coefficient at certain wavelength band. Also, as you can see, the CVT adds this zero padding at the beginning and end of the wavelet. And this affects signals that are discrete, like spectral signatures. Therefore, we also calculated the cone of influence, where this zero padding affects the spectrum. And as you can see, the padding gets larger with larger scale, so with larger scale, the cone of influence affects more coefficients, so we have less reliable coefficients as larger scales. And even if we would take even larger scales, then the whole spectrum would be under the cone of influence, and we would have no reliable coefficients. Additionally, CVT requires continuous values, which means that we need to have uniform sampling interval. However, the Nmap data is not actually uniform, as the sampling between bands changes a bit. Therefore, we created this three-way process where we separated the spectral data to three different regions: the visible near-infrared, shortwave infrared 1, and shortwave infrared 2. Then we interpolated each of these regions to even spacing, matching the average original spacing, so that there was still the same amount of bands as with the original data. Then these regions where the CVT was performed for each of these regions, and finally all of the coefficients were added together, so we had the scalogram for the full spectral range. So here's an example how the spectral data looks as a scalogram. And because we had three different regions, we needed to add the cone of influence for at the end and at the beginning of each of the regions, which is why this is how the scalogram looks like after the adding of the cone of influence. Here at the end, we also have how the spectral signature looks like at one scale. Here is the scale 8. If we go to the next one, then we have scale 4, and then in the next one, scale 16, so it has a bit different look at each of these scales. Yes. So in conclusion, hyperspectral Nmap data outperformed the multispectral Sentinel-2 data for peatland surface monitoring, and the continuous wavelet transform was the most promising of these methods. However, we do acknowledge that in future research, expanding the reference data set would give us even better results. Thank you.
Thank you. So, are there any questions in the audience? If not, I could have one. So, you showed that the moisture index was performed like it was like the results were worse than for the other parameters. So, do you have a reason for that? So, why the moisture index is so difficult for the model?
I would say, well, because we had data from such large regions, the using just single bands that the moisture indices use doesn't really capture the actual moisture variation in such large regions. So the moisture indices might work if we only have data from one peatland site, but because we have such a large gradient of different sites, these one or two band indices doesn't capture the full moisture conditions.
Okay, thank you. If there are no additional... there is one question, yeah. Wait for a mic, we need a mic.
Yeah, hello, I'm Petri Välisaar from the University of Vaasa. Thank you for the presentation, and it's very interesting indeed to use the multispectral data for analyzing these kind of moisture things, for example. But I was wondering that what is the motivation of using the wavelet transformation? I guess that if you use some multispectral regression methods, you could also maybe do without it, like something like extra trees regression or some neural network methods. So what is the motivation of using wavelet transformation?
Well, for me, the motivation behind the wavelet transform is, well, first to see how it works like this, but for the next step, I actually want to see if we can create the moisture index where we are using the wavelet transform values, as they use more bands than just the certain 1 or 2 band combinations that normal moisture indices use. So in the wavelet transform, as it takes a lot of bands into account in one wavelet coefficient, therefore it might provide us better moisture indices in the future. But yeah, here we are testing how it works on its own. But yeah, maybe we can further use this to create moisture indices that could work just as a simple linear model.
Okay, thank you. And now it's time to move forward in the program. So we welcome Arja Alinejad from NTNU. And he will talk about the calibration and validation for a hyperspectral small satellite constellation.
Yeah, okay. Yes, so oh, that's a bit too loud maybe. I'll be talking about the calibration and validation of the HIPSO small satellite constellation. That's also a mouthful. And I'm a PhD student at the Small Satellite Lab at NTNU in Norway. And I'm quite new to the field, so please ask questions and come with critiques. I might learn something from it. Here you can see in the bottom some of the pictures that our satellite has taken. This is the overview. I don't think I'll use time on that. I think we're a little bit behind on time. But to start with, the motivation. Moving forward, there will likely be a lot more satellites in orbit. And with new space, you might also have some smaller actors that are sending up satellites. Furthermore, we will probably have more small satellites and small satellite constellations as opposed to big satellites. And all of these small satellite constellations will need calibration. So here I'll talk about calibration of hyperspectral Earth observation small satellite constellations in particular. And we'll likely also see a move towards more hyperspectral moving forward, as we've seen that has been quite useful, for example, distinguishing cytoplankton types and that kind of stuff. And with new space, we'll likely also have actors that don't have as much time and resources as NASA. And the satellites, since they're small, will likely not have onboard calibration devices. So it makes sense to develop effective, both time and cost-effective calibration effort for small satellite constellations. So a little bit about our satellites first. They're called HIPSO 1 and 2. They're small satellites, both of them, with identical imager designs. Both are 6U CubeSat, so quite small. And they have push-broom dispersive hyperspectral imagers. So this hyperspectral imagers type is slightly different than what Hyperfield has, for example. And the type of imager is quite important when it comes to the calibration. We have between 400 and 800 nanometer bands and 120 band which come from binning more bands and ground resolvable distance of up to around 100 meters. And the two satellites were launched in different times. The first one came in 2022 2022, and the next one 2024. So the first one has been in orbit a bit longer than the other, and that also plays into why it's important to calibrate them so that we can use the data of both interchangeably. Here I just want to quickly say that the data is available and we can task the satellites ourselves, so it's possible to request captures from these. They have global coverage, and we have also developed a Python package for processing hyperspectral data, which is also freely available. Yeah, you have the QR codes there. I'll also add them in the last slide. Here is just some sample data that shows some of the hyperspectral data of our satellites from HIPSO 1 and 2. And then I'll jump into the calibration. First I'll talk some about the data that we've used for calibration. Lunar captures have been very important for the calibration, and they have been used for spectral calibration, radiometric calibration, spectral resolution, post-launch movements, and artifacts. And here we've used ESA's LIME moon model for comparing our moon measurements with some ground truth. And we've also used uniform desert site, being Libya 4, for small and post-launch movements. We've used RadCalNet sites for validation. We've used a lake in the US for resolution, and some captures of the ocean for SNR. So first of all, we'll talk about the most simple calibration, or the most simple changes that might have happened. Since when you have a hyperspectral camera, you usually calibrate this in the lab and you have coefficients. But when you launch it, things get shook and moved. So here we look at potential horizontal and vertical movements that might have happened from launch. For looking at the vertical movement, for the HIPSO satellites in particular, there is a dark bar in the top. So there we can assess the position of this and see if this is the same before and after launch. So to the left, you can see a frame from a capture of Libya desert site. And you can see that the top bar has moved slightly. So we know that there's a vertical movement. Furthermore, we can also look at horizontal movement by looking at the spectra of the moon and comparing this to the spectra of the LIME moon model and see if we see some movements here. And we can fit a polynomial to see what kind of shift there has been. And from this, we see that for the HIPSO satellites, it's mostly a static offset. If you see more of a curve, it might show that there's been some tilt of some of the components. But after we've assessed that there has been this much vertical and this much horizontal movement, we can from there adjust radiometric coefficients, because these coefficients are particular to each pixel. So if stuff has moved, the coefficients also need to move. And after moving the coefficients, we evaluate whether this improves the data or not. And for this, we use LeCrau and Gubabeb, which are RadCalNet sites, and we compare to the RadCalNet movement measurements in addition to PACE, the NASA satellite. And the blue and the red lines are HIPSO. And here we can see that there is some reduced noise in the bands, which shows that the move of the radiometric coefficients actually helped. And this is a quite easy thing to adjust, so the more simple adjustments are usually the best. Furthermore, we can use this exact same analysis to also adjust the spectral coefficients. The spectral coefficients being which wavelength you have at each pixel. The radiometric coefficients are how much light intensity each pixel is attributed to. So here we can use the same LeCrau and Gubabeb sites, and we can look at the oxygen band, because this has a certain position. And we can see that before moving the spectral coefficients, the dip is a bit off, but after adjusting them, the dip adjusts more nicely. Furthermore, we can also use the moon captures for radiometric calibration. Here we compare the modeled moon spectra from the LIME model with HIPSO 1 and HIPSO blue and HIPSO 2, sorry, in red and blue. And here we can see that HIPSO 1 has a slight dip in the first few wavelengths. So then we can develop some gain coefficients which adjust for this, making the data of HIPSO 1 and HIPSO 2 more interchangeable and similar. And again, we can assess this on the Lacroix and Goba websites, and we see that after the adjustment, HIPSO 1 and 2 and blue and red agree more. And this is quite important because when you have a satellite constellations, you usually want to be able to use the data interchangeably, and also when the data can be used interchangeably, you can build models that use the data for both of the satellites, if you, for example, need a sea-land clouds classifier or something like that. This also means that after HIPSO 1 is done with its orbit, when it deorbits, the data from this satellite is still useful for us because we can use it to build models for HIPSO 2 also. Furthermore, the moon can also be used to assess artifacts. It's very nice because there's a very bright target against a dark background. And here you can see the spectra of the moon in blue and red. And what we can see is that there's some spectrally dependent smearing or crosstalk, meaning that the signal kind of smears out as we go up and down in wavelength. You can see that more clearly in this capture right here, where I've tried to make it extra visible. And this kind of artifact is also important to assess and notice because given this, we can't, for example, use a simple moon mask to get the moon signal because the pixels are switched or you get signal smearing out. And in the spectra, you can also see a small bump, and this is ghosting. So here I've also increased the intensity a lot, so it looks worse than it is. But from looking at the moon here, you can clearly see that it's a flipping of the moon. Luckily, looking at ground targets, this is not very significant on Earth, but this shows that the moon can also be used to assess these kind of artifacts. Furthermore, we can use the same Libya desert site that we used previously to also assess SMILE in orbit. You might have SMILE coefficients in the lab, but after assessing them in orbit also, using autocorrelation and a polynomial fit, we can see the SMILE or the bending of the different positions of the wavelengths for HIPSO 1 and 2. And using these new coefficients, we see that there's less of a bend in the spectra. It might be a bit hard to see here, but if you follow the white line and the dark line beside it, you can see at the top there's a bend, and this is corrected for after using the SMILE coefficients. So the same Libya desert target can be used for this also. And then I'll quickly go through spatial resolution, I mean an SNR. Here we can use a bridge that has a width that's smaller than our ground sampling distance. And using this, we can assess the line spread function. And here we can see that HIPSO 2 in blue has a bit better ground resolvable distance than what we have in HIPSO 1, which we can also see if we compare them visually. You can see that HIPSO 2 is slightly sharper. And this can come from the experience that we got assembling the first. The second was assembled more carefully and also calibrated a bit more carefully, and you can see that this has an effect on the spatial resolution. And SNR was assessed using uniform ocean targets. I forgot to say that earlier, but our satellites are mostly geared towards the ocean and monitoring the ocean. So that's why we use the ocean to also look at our SNR in a dark ocean patch. And here we can see that HIPSO 1 and HIPSO 2 have quite comparable spatial and spectral SNR. So in conclusion, we can see that we can use the moon and a few ground targets to do a simple calibration that's cost effective for satellites that don't have onboard calibration devices, where, for example, the moon can be used for several different purposes. And this is a paper I'm currently working on, and it's in the first draft, so if you guys want to have a look at that, you can contact me. This was probably very quick and a lot of different things at the same time, but please do contact if there's something, and also here are the links to the data, website, and Python package, so you can contact us about the data and stuff like that too. Yeah.
Thank you. Now it's time for questions. Do we have anything in the audience? If not, so I could ask maybe, because I'm not, this is not my field of expertise really, you mentioned several times, for example, the COPA website in Africa. So what makes it so special that it is used, it is good for calibration?
A good question. It's one of the sites, RadCalNet is a calibration network that they have measurements on the ground where these measurements are also extrapolated to the top of atmosphere, and they have decided to measure sites that are quite static over time. So they call them pseudo-invariant sites, meaning that if you capture it now and in 1 hour, it shouldn't change too much. And typically they're also sites with less atmosphere and clouds. So because of their consistency, they're quite useful for calibration.
Okay, thank you. There's one question.
Hello, Matti Matus from VTT. I was wondering about the temperature stability of the things. I would expect calibration, especially on this small satellite, to depend on the temperature of the sensor and also how the whole structure expands and contracts in space as it goes in and out of the sun. Have you looked into that?
Actually, no. The temperature is something that we haven't really looked into, at least yet. But it's something that might make sense to look into. Personally, I don't know too much about how this instrument would change with temperature, so might be worth checking out.
Okay, so if there are not any more questions, so we thank you once more. And now it's the time for today's session's last talk, as we had a little bit change of a program. So the next speaker will be Arne Hovi from Aalto University, and he will talk about the multi-angular spectral measurements of 3 branches.
Okay. Yes, thank you. Good afternoon. So I represent the remote sensing research team at Aalto University. Yeah, spectral libraries, they are nowadays more and more common in hyperspectral Earth observation. Here is an example of a spectral library of a forest comprising of many different targets, which each have different spectral properties. And as I said, these are more and more common in remote sensing, and many research groups, also our group, have collected the spectral libraries. But the problem is that even though we are talking about reflectance spectra, so in reality we are measuring reflectance factors which depend on view and illumination geometries. So ideally we would like to have BRDF libraries that allow you to calculate reflectance factors for any application. And now we are building in our spectral laboratory this kind of facility that we can acquire BRDF spectra for various vegetation targets. But in this in this presentation, I focus on one type of samples, which is 3 branches, which are quite challenging to measure because of their small size and curvature. Here is our measurement setup currently that we used for the branch measurements. It consists of ASD spectrometer, then receiver and illumination optics, and then motors that can move this receiver and illumination source. Yeah, this is just to mention that, of course, we are not the first one to build goniometer. There are several already existing with a little bit different designs. Our purpose is mainly to build this facility in our laboratory and have a versatile system that covers all the wavelengths all the solar wavelengths, and also can measure different sizes of targets. But if we talk about these small targets like branches, maybe the main choice that you have to make in the beginning when you build this system is that you can basically have two different configurations. Either your illumination is larger than the receiver field of view, or the illumination is very tightly focused. And we chose the latter one for the branch measurements because it makes it possible to define clearly the measurement area, and also that the area doesn't vary depending on the view angle. But this was actually particularly challenging, and we struggled quite a lot with it because we have this broadband halogen lamp and then relatively large diameter fiber optic cable. And how to focus the illumination from this, it was really a headache, and we spent a lot of time, but finally we found a solution, which is this curler illuminator with several lenses. Just very shortly how it works. So basically, if you have one lens, it can collimate the light beam at one focal length. Unfortunately, if you want to collect a lot of light, you have to have short focal length. You have to have the lens very close to the sample, which is quite impractical. But then you can have additional, like focusing and recollimating lenses with longer focal length, and that makes it possible to have longer measurement distances. And then in our current system, we also have this restrictor that can adjust the beam size, and we can have a illumination beam that is down to 0.5 centimeters approximately in diameter. And yeah, here is how it looks, the final version, and on the left-hand side you see the light beam, and we were very happy when we got this ready. It's maybe the most perfectly collimated light beam I have ever seen, so yeah, this was very successful. Then for the receiver is basically just a fiber optic cable, but we have a similar curler illuminator system there also, just turned upside down so that it's collimating the light or illumination from the sample to the detector, so that all the spectrometers, detectors obtain uniform illumination, and this ensures that the spectra are continuous without any discontinuities between the detectors. Okay, that was the system very shortly, how it works. Then, yeah, this is how we calculate the quantities. This is quite standard stuff, so I'm not going to explain it, but I just say that we measure the BRFs, bidirectional reflectance factors. And we tested this system by measuring Scots pine and silverbird's branches, 3 branches per species. We had two illumination angles, 11 and 45 degrees, and 28 view angles spread over the hemisphere. And the size of the measured illuminated and measured area is 6 millimeter in diameter, so it's very small. And the measurement distance is 13 centimeters. Here is the how I will present the results. So we have 2 illumination angles, and to simplify a bit, I present the results only for the principal and cross planes, and here it's on the left you see how they are defined. So in the principal plane, plus is the backscattering direction and minus is forward scattering direction. And I should mention that we cannot go very close to the hotspot with the current setup, so we had to replace those hotspot angles with nearest possible view angle. And also the spectrometer can record from 350 to 2500 nanometers, but we cut the beginning and end because of the noise in the data. Before measuring the branches, we measured spectral on panels just to verify that the configuration works. And maybe easier to illustrate is just to take one wavelength from there and look at the BRDF shapes, and we compared it with measurements made by others previously, and these qualitatively they match quite nicely with previous measurements. Then we can also, because we have measurements all over the hemisphere, we can calculate the hemispherical reflectance, and we compared this to the calibration certificate, like independent measurement. Okay, currently we have 3% difference, so it's not perfect, but it's quite good, I would say, and we can probably still improve slightly by improving the alignment of all the components in the system. Yeah, then the branch measurements, pine samples. First pine sample looks like this. What we observe, the BRDF is relatively stable, but then in the forward scattering direction there is quite strong specular reflection at high illumination zenith angles. Okay, second sample looks quite the same. Then the third sample was a bit of an outlier, so again the principal plane looks the same, but then in the cross plane there is quite high asymmetry. But if we look closely at the surface, so we notice that there is actually some irregularities in the sample, so this might be just a coincidence. Then birch samples. Generally we notice that birch has a much stronger specular reflection compared to pine. We also notice quite a strong anisotropy in the cross plane, whereas pine was quite flat BRDF. And yeah, the samples, two first samples look almost the same. Then in the third sample there is much less specular reflection, but you can see even by eye that the surface for this particular sample was rougher than for the others. Yes, and then finally we can also calculate the hemispherically integrated reflectance for these branch samples, and we compared them with measurements made with an integrating sphere. Theoretically they should agree perfectly. These are not the same individual samples, so there is obviously some differences, but at least they correspond roughly to each other. So everything seems to work nicely. And then finally we can look at these hemispherically integrated reflectances sample by sample and compare the two different illumination angles. And what we generally observe is that when the illumination zenith angle increases, the reflectance increases, absorption decreases. But there are also a few outliers, which I already mentioned. To conclude, we have built an automatic goniospectrometer capable of measuring the spectral BRDF and directional hemispherical reflectance of small vegetation targets at full short wave range. And maybe the implications for remote sensing we can draw from these preliminary measurements was that the tree-branch BRDF is highly anisotropic with strong forward reflection, which means that these BRDF measurements should improve the remote sensing models. And then another quite interesting notion was that this hemispherical reflectance depends, and absorption depend on the illumination angle. And challenges, I can say that these branches are really challenging because of the rough surface and curvature. Also, I can mention the measurement time in the current system. So one branch took about 2 to 3 hours to measure. So it's relatively slow, and if we plan to collect these BRDF libraries, so the sampling design has to be very carefully planned. So you cannot measure BRDF of all samples, but maybe just some small subset of your samples. And next, we are still planning to expand this system so that we can, especially the illumination source, so that we can measure larger targets also. But that's it. Thank you.
Thank you. So, do we have any questions in the audience? Nope. So I could maybe ask, so are there any other applications for, this seems like a very fancy device, and so you mentioned the remote sensing, implications on remote sensing, but are there like, could this measurement tell you something about the tree health, or I don't know, is there any these kind of applications for these measurements directly?
Yes, of course, the spectral data could be used for assessing the, for example, tree health or biodiversity. And yeah, if we think about like broader application, I've seen, for example, computer graphics people, they are acquiring this BRDF spectra.
Okay, thank you. If there are no other questions, so I think we thank you and also at the same time all the speakers in this session. And now it's time to get the coffee in the machine, and then we continue with the EO Future Mission session at 15:35.
have now so many missions that this is less easy to arrange this part, because we have so much flying and there's so much to tell what we are doing with the missions that are already there. So I'm really happy that we still can keep one of these future-looking events here, or kind of like the content is about what could happen in the future, and we will. I guess the time is not yet, so let's not be too hasty. But yeah, then just entertain you a while. And also the sponsor list nowadays is so big, because I think I have been from the first one on in this event as in the organizing committee. And I would say that first time we had 3 lines, then we had 4, so you can always say that 1 line has been added each year. So in 4 years' time, we are out of the space in this slide template. And that's a great, I think, thing to happen, and really happy to see more of you all the time. And what I hope from you is more questions. Like everybody, it's great for you to tell about yourself and through your question to present what you're doing. That's all fine. So please try to do that in this session. And I guess now I have taken the time that we can be perfectly, not yet, still some seconds to go. But are there still people on the corridor? I don't see people coming in. So if everybody is in the room, then let's just start. So, future EO missions is the topic. And in this case, I think we have, let's say, a nice update of some developments, but also something really new. So something for everyone. And we start out with something called Aquatime, which actually is like expansion missions from Sentinel satellites, CHIME and LSTM, that we are already preparing now for them. We have Sakari Väkevä from the Finnish Environment Institute. Please go ahead, push the button, and then the microphone goes on.
Good afternoon, everyone. I'll be introducing the project Aquatime. And Aquatime focuses on how the upcoming Sentinel expansion missions, CHIME and LSTM, as Mikko just said, how they can be used to support the understanding of aquatic ecosystem phenology. And phenology means how phytoplankton, well, let's just talk about algae, how algae communities behave during the growth season. Because in the springtime there's usually some kind of alga community, and then in the summer there's some other kind, and how these things, how the communities change depending on both the season, availability of nutrients and so on, and how to map all of this from Earth observation. So I guess the motivation is also quite simple to understand. And knowing more about the aquatic phenology, knowing more about these organisms gives insights into ecosystem protection, lake management, and so on. Aquatime is a highly collaborative project. We have this kind of list of project partners. The coordination happens from Brockman Geomatics in Sweden. Then we have project partners from Finland, Sweden, Germany, Estonia, and Belgium. And this project was funded via ESA's Future EO Call in the SUP, or Sentinel Users Preparation Framework. And that means that even if these missions don't exist yet, the funding is intended so that we can prepare our users, the methods, and the data use, so that when finally the satellites will be launched, the community can immediately adopt them and start using them for their purposes. As was mentioned already a few times, Aquatime has in particular these 2 upcoming missions in mind. So CHIME, which is a hyperspectral mission, and LSTM, which is the thermal, infrared, and other infrared qualities in mind. Stopping here briefly, CHIME has a 30-meter spatial resolution. You can see on the slide also the wavelength range, and maybe the wavelength in parentheses is the important information. So also the spectral bandwidth is quite narrow, not as narrow as in many other missions, but still should be sufficient for aquatic purposes. And the swath width and the revisit time together mean that the revisit frequency at our latitudes will be about an order of a week once the 2 satellites are in orbit. And the first one is set to launch by 2029, perhaps, with a very big question mark after that. And yeah, let's move on. So the core of Aquatime is to prepare sort of value-adding products for these missions, even though they don't exist yet, only in the like laboratory at the moment, so that the uptake of these missions can be rapid once they are in the orbit. As part of this, we make a so-called representative dataset, and that means that we try to describe or depict how the study areas behave throughout the year, using as many variables as needed so that it's sort of fully represented. And then we do forward modeling with radiative transfer modeling from that, so that we get an understanding of what the satellite would observe. So we sort of simulate an observational scenario. However, we also try to make innovative products at this point from the data, and now we have to acknowledge an important limitation. So, as I said, CHIME alone doesn't have a sufficient revisit time so that we could focus on the quickly moving, quickly changing phenomena. So we have thought so that it's important that we incorporate Sentinel-2 and Sentinel-3 data as well. So our product design, for example, it takes into account both CHIME and then the other already existing missions to get the temporal continuity that will be required by the use cases. So this slide shows a flowchart of our concept, which I actually referred to already. But our study sites have continuous data collection even now, even today, and also high-density field sampling, so we know the areas well enough so that we can do this forward modeling and synthetic data generation from that. We use MOMO mainly for the biooptical and atmospheric radiative transfer, and then hydrolite for some use cases. And that gives out the representative data set for the mimicked CHIME or LSTM data, and then starts the product planning, information product generation, so that the users can have something then from these already now that the satellites don't exist yet. So we have collected, I'm not going through this list in too much detail, but this has been collected from stakeholder discussions, which was part of the project as well. So many stakeholders would like, of course, better retrievals of basic water quality variables like chlorophyll, CDOM, and so on. But what CHIME especially allows is the identification of optical phytoplankton types, algal groups, maybe better biomass estimates, and these kind of things that multispectral data don't necessarily provide. Here you see the case studies and sites of the project. Most of these relate to case study 3, which is lakes and rivers on the European area, and all these places, or almost all of these, have continuous water quality measurements, which give a strong basis for the method development. But case study 1 focuses on so-called nuisance blooms of Phaeocystis globosa on the Belgium coast. Then there's one mussel farm case, which is this number 2 in Dalarö, Sweden. And then we study also the effects of climate change at Uutö, the outermost island in Finland, and that's case study 4. Just to show an example of what the representative dataset looks like, in Lake Pyhäjärvi here in Finland, which is a medium-sized, very circular lake with a long eutrophication history, there has been this continuous monitoring station since early 2000s, and with the current instrumentation since 2019. And it's active every year during the open water period. And there we collect FDOM, turbidity, temperature, and then there's this kind of total algae sensor. It's kind of interesting sensor. It has 2 LEDs, and it excites the phytoplankton with 2 wavelengths. So the phycocyanin and chlorophyll excitation wavelengths, but it only measures at the chlorophyll emission. So it sort of gives how strongly the absorbed light is passed on to the main photosynthesizing pigment, which is chlorophyll. Quite difficult data actually to use in practice or to interpret. But with this kind of data and using also the cellular inverse microscopy observations, we can partition the total chlorophyll from the continuous sensor into the algal classes. And we of course need this partition, how much of chlorophyll is in blue-green algae, how much is in diatoms, to be able to make this forward modeling of the spectra and to pass them on to the atmospheric level. To sum up together, we don't have any real data yet, obviously, because the missions don't exist or they exist only in the lab at this stage. But within our project, we will also release the representative datasets openly so that you can also use them in your own method development ventures. However, our information products also include Sentinel-2 and Sentinel-3 to take benefit of the good temporal and spatial coverage of the currently existing missions as well. Thank you. With that, I conclude, and I'm happy to take also any questions you have.
Thank you, Sakari. Well, thank you, Sakari. So, I invited you to be prepared for questions, so is there anyone? Because you put me always on the bad spot, and I need to have then a question. Okay. Well, I do have a question in the sense that we do also have these contributing missions, so kind of new space activated in Europe for these kind of measurements as well. I think with Kuva Space, we actually have the only one with hyperspectrals in Finland even. Yeah, so how do you see that this could also kind of help each other in this activity?
Well, of course, the technical specs of the instruments differ also quite a lot from each other, but the spatial resolution is similar in both missions. And of course, with Hyperfield, we can plan ahead sort of the observation scenarios and the kind of data that we will encounter later. But of course, the technical specs are somewhat different between the instruments, so the methods might not be directly transferable. I'm talking about things like wavelength, range, and bandwidth, and so on.
But just as a comment, I think that still is an opportunity when you have those test areas and you have those other in situ measurements, for example, in these places. That's, I think, a good invitation to try to mimic things from Hyperfield there as well. So anyone now with another question? No, tough crowd. It's the afternoon.
It's all right.
Yeah, it's fine. Thank you, Sakari.
Thank you.
If we don't want to bother you more, yeah, give him another applause. But he leaves us now lots of time for the next presentation, so you're free to use more. We have a great company in Estonia, Kapazeta, and they have an excellent idea which needs to be put up in space, and Martti Jussi is going to tell us about it. Go ahead.
Yes, thank you. Hello, everyone, for the third year in a row. So here I am again talking about another mission that is still, how did you say? In the lab or on paper. Doesn't exist yet. So, I'm Martin Jussi from Kapazeta. This one doesn't work. Okay, it does now. Kapazeta are a leading SAR expert company from Estonia. We are now more than 10 years old. And we're traditionally like an EO service company. We're the world's first EU farming subsidy claim compliance monitoring system provider. So we started our business in the CAP monitoring domain, if you know what it is, but in the public agriculture domain. Now we've expanded our business also into defense and forestry over the years, and we still do a lot of R&D, mostly together with the European Space Agency. and now also have a mission concept in development. Now, what the problem is, like last years I've been telling you about carbon credits. Now I'm still telling you about forests in a slightly different context as the contexts change. But the fundamental here is that the importance of forest doesn't change. I mean, the climate change is not going anywhere, and the forest as a resource, and forest as a food security and also a national security enabler will always stay there. So for food it provides stability, irrigation, particularly in harsh climate areas, and for national security, particularly in our regions, it shouldn't be a question why the forest is important. But the problem still remains that often the information about the forest is outdated, it's fragmented, and also sometimes public organizations in the same country don't have the same picture of what's going on with the forests. Well, the Earth observation is an obvious solution to this problem. I mean, there are a lot of missions and even more applications focused on solving this issue. So monitoring the forests for simply whether the forest is still there, so clear-cut detection, but also trying to measure the height, the volume, timber stock, carbon stock, all these parameters from forests, and doing like remote sensing-based forestry. But what is really critical there is the height dimension. So you may as well know, I mean, traditionally forest height from like forest remote sensing, the height is usually measured from LiDAR, but there's another good option to also get it from bistatic or multistatic SAR data, so having more than one SAR satellite receiving the same signal, so one of them could be transmitting, well, I mean, one of them has to be transmitting, but both could be receiving, or one could be receiving, so effectively you get a stereo SAR image from space. A good example of such mission is the TandemX, the German TandemX mission. But this multistatic SAR is still not, I mean, it's not mainstream, it's not, like, not everybody's using it, and the reason is that the technology is quite complex and there are not many missions implementing multistatic SAR. No. Why did this stop working? Okay, yeah, well, just more than now approximately a 10 years old figure of how these two correlate. I mean, you can't see too well from the image, but if you look at the graphs. Okay, do you need to click or do I need to click? Okay, but from the graphs you see that the correlation between these two, like if you look at LiDAR as a reference, LiDAR that is widely known as a highly accurate source of height data, comparing it with SAR coherence from TandemX, you can see the correlation is pretty good. There is a more recent image from our work in Kappa Zeta, is actually from last year, so 2025. It's just the images are a little bit older, so we did some analysis with the TandemX data, and when we looked at a recent TandemX image, and we had our initial reference data from 2022, and you can see from this image that the forest there is intact, but we had a TandemX image overlaid to this area, and you can clearly see that the INSA height has a kind of an anomaly here between the C and D. So this is this area. And when we looked at the more recent reference image, you can see that there's been a clear cut. So this clearly shows how well you can measure this from multistatic SAR. Now, it's bistatic in the case of TandemX, but it's actually multistatic in case of our concept. So how we are trying to solve the issue of not having enough three-dimensional SAR data, we are developing this mission that could as well as be a Copernicus expansion mission, but it's not yet there. So we are planning to fly 3 passive receivers in formation with an active SAR. For the first generation, it will be Sentinel-1, and the idea is to generate this multistatic or 3-dimensional radar images by receiving the Sentinel-1 signal from different angles. And by doing that with 3 satellites, we could do interferometry, but we could also do some let's say, very, very rough tomography. And with this, we would get a global forest height and volume information approximately monthly. It's even bi-weekly with a single Sentinel-1, I mean, with a 12 days revisit globally. And it's a quite cost-effective way because the receiver satellites are much easier to build than the actual transmitter satellite. So the antennas can be a lot smaller and a lot simpler due to the fact that they're receive only. So we are aiming at an approximate mission cost of 40 million, which is around 20% of a single Sentinel-1 satellite, and providing effective height and volume measurements globally that we could sell to multiple market segments. I'm not going to go in the market today, but there is, of course, there is one constraint. So global is not really global, so we are constrained by the Sentinel-1 footprint. This is model based on Sentinel-1A, but the Sentinel-1C has a slightly different footprint, and you can see that you can't really cover all the forests in the world, but still the critical areas where forest is seen as a resource can be covered quite well. So where we currently are, we are in phase A in a consolidation study with a quite nice consortium. So it's us, a company from Estonia called Rantelon. We have TU Delft on board, Nanoavionics from Lithuania, Serco from Germany, and we are working with ESA. And the ESA people are not simply just funding the study. The engineers from ESA are actively contributing to our mission. So it's a very good collaboration between the consortium and ESA there. And I'm here also mentioning an Italian SAR expert company because we are about to onboard one more member to the consortium, but the contract is not signed yet, so I'm not going to shout out the name. But if you know the sector, then there are quite usual suspects that you could think of there. So far we've also, we also had a lot of stakeholder interviews last year. We consolidated our user requirements, derived mission and system requirements. And we're shaping a technical roadmap for validating these requirements and performing analysis and simulations for de-risking. So it's kind of a, let's say we could call it a rigorous a systems engineering exercise at this stage. And one reason it's still a rigorous systems engineering exercise is that we don't have the next phases funded. And we are currently at a phase where if we want to move on fast, we would need to commit a lot of costs. So we've already done quite a bit of analysis, and we are quite confident to basically purchase the satellite bus and start developing hardware. But that needs funding to be committed. So as of now, we will have a requirements review with ESA on the second half of February, and we are also actively trying to raise funds for the next phases. So some types of analysis and simulations we've been doing for de-risking. So first of all, you could, if you want to retrieve SAR signal and you want to process it, you want to generate a multistatic image, you need to synchronize the signals. So a lot of it you can already de-risk on the ground without actually launching something. So we've been doing it with software-defined radios. And with that, we could give the Sentinel-1 signal, and we could also try to do initial sensitivity analysis that would feed into payload design. we could basically prototype the SAR focusing steps on the ground. We could do time and phase synchronization because we need to synchronize the phase between the receivers. And also the clocks will eventually be drifting, so any compensation methods we could already do on the ground. So there's a lot of things we can do without actually launching anything. And we've actually acquired now the direct signals from Sentinel-1, and we're actually also planning to acquire the reflections to actually try to do some focusing. Fortunately, also we have our good friends from TU Delft who have specialized software that was initially developed for the ESA Sesame mission and also now being used for the Harmony mission, which is particularly designed to simulate this kind of receivers to a large illuminator such as Sentinel-1. So we could model the orbits, we could select the most optimal configuration in space, and we could also simulate the performance of the payload in different predefined configurations. So we're looking at an antenna of approximately 2 by half a meter, and we could see how that would behave in space when retrieving the Sentinel-1 signal. So here on the right, you could actually see a simulated single-pass SAR coherence image if we would retrieve it with a 2.5 meter antenna. So these kind of simulations we could do, and we could optimize the payload based on the simulations. Well, I mentioned that this mission is also based on stakeholder needs or user needs, so this is eventually a commercial one, and what the users want is products, not a mission. So their need is actually having a long-term source of forest information coming from space, and the multistatic data is just an enabler there. So the long-term roadmap can be pretty much well enabled with the existing Copernicus program and the planned satellites in the future. And eventually it would make sense also to develop a dedicated illuminator to get rid of this dependence of an existing illuminator. But yes, currently we are working on the Sentinel-1 co-flyer mission. We would, realistically, we are now looking at the launch sometime in 2030. And before that, we would actually also fly a precursor to validate some of the technology, particularly the payload in orbit. So, but the real need is having a systematic long-term information on global forest stock and how it's changing in time. And that will definitely contribute to better knowledge on how the climate is changing and how the environment is changing where we're living in. So that's it from me. Yes. Thanks so much, and open to questions, discussions, etc.
Yes, thank you very much, Martin. So anyone know Italian SAR company? Yeah, anyway, that's not the point I want to make. I want you to now have a question. Anyone? Obviously.
Come on, I've had questions from you every year.
Yay! Excellent. Go. Thank you very much for this step.
Would this be able to monitor other deforesting actions such as active forest fires?
Such as, sorry?
Ongoing active forest fires or other natural disasters.
Fires. I mean, if there's a significant decrease in the volume or the height of the forest, then this can be seen, yes. It's really not seeing the event of burning, but it's seeing the event of decreasing volume. Yeah.
So it started with the question. So anyone else? We still have time for it. Timo.
Thank you. there was a comment from the monitoring society in the rainforests that the people there are actually cutting the forest below the top folios and
Yes.
preventing the satellites from seeing this one. So do you have actually counterproof of actually being able to detect these kind of forest cuttings?
Theoretically, again, this is possible because with bistatic you can see the change in the volume. So if the total height is not changing, but the volume is changing, then you could still see it. It's an interesting application that we'd really like to actually test. We don't have proof that it works, but theoretically with the bistatic SAR, I mean with the volume coherence parameter, it should be possible. Yeah.
Yay! So, but that was a very good session. Thank you very much, Martin.
Thanks
Give
so
him
much.
another applause. And then we can go to the next one, which I must think this was about the Hyperfield 2 mission, wasn't it? Malahati Eskola, yes. So in a way, reflection to the first presentation can now happen already in this one. So please, go ahead, Malit.
Hello, good afternoon, and thank you for your interest. I'm Mala Eskola, Commercial Director at Cubaspace, and for the next 15 minutes I'll be talking about Cubaspace and our solution. And to summarize, our aim is to develop a constellation of hyperspectral satellites and in-house automatic AI-driven analytics platform to deliver near real-time insights. So the world is changing fast. We're entering a decade of climate instability, geopolitical tension, and resource insecurity. Yet what we lack is near real-time understanding. To effectively mitigate a lot of these changes, we need to shift our mindset from tasking a satellite to actually bringing information as an always-on format. So this is exactly what Cubaspace is aspiring to do. Moving from just delivering imagery to actionable insights. And at Cubaspace, the goal is to deliver it within 10 minutes for fast response applications, and then for always-on, less time-sensitive applications within 1 to 2 hours. So by 2030, our goal is to launch 100 satellites, to be able to monitor wide area consistently, and with high frequencies. So for example, over this part of the world, we're expecting to have a revisit of 2 to 5 times a day, giving us the opportunity to process this data near real time and to provide information across various industries. And how we do this, again, I want to emphasize, is the use of AI natively. Maybe some of you already know about hyperspectral. This is, of course, a space event. But if you allow me just to briefly take you through the different modalities that you might be familiar with. So first of all, and how hyperspectral is different from these modalities. So let's start with radar. So a technology that was just presented as well. It provides information on texture, not necessarily able to define or identify the material that the object or target is made of. Of course, it's capable of seeing through dark and nighttime, something that hyperspectral is not able to. When it comes to RGB, and multispectral, it has lower spectral bands, which means that it can see objects and changes that are visible to our eyes, to human eyes, but not necessarily beyond that. When it comes to infrared, it is based on thermal differences and it has night vision. But again, much like radar, it won't be able to see what the material is made of and what are the changes it's undergoing from a material level. Here comes hyperspectral. We call it and we recognize it as the missing spaceborne capabilities today, certainly on the mainstream field. hyperspectral allows us to actually go at a biochemical level to understand what materials are made of, whether it's man-made or natural materials, and fully understand the way in which it's morphing and changing its format. A bit about the technology itself. It's two-pronged strategy. We have this hardware and the software. On the hardware side, hyperfield satellite is going to be the central part of our constellation. The image that you're seeing here is our second generation satellite. The wavelength that we're working towards is from 450 to 1,650. The spectral resolution is about 20, and then the GSD, the ground sample distance, is about 15 meters. And the swath is with near is going to be 30, and with the near it's going to be 20. So one of the things when it comes to hyperspectral that you might be familiar with is the data quality. You need to have a pretty high data quality to be able to develop applications, especially in certain areas, for example, the marine domain. And so with our platform, what we are aiming to do is to reach, to be in the range of 100 to 650, which is pretty high in the standards of hyperspectral. As changes are happening faster and more frequently, one of the things that we are trying to improve is the latency of getting data into insights. And so we will have onboard GPU that will allow us to run AI models in space to be able to process this data almost instantaneously as the data comes in from our sensors. And once the data has been processed, we'll be able to actually send this data down to the end users, whether in the form of text message or through other means, through set-to-set communication. This is going to expedite the level at which we will be delivering information, for example, for the first frontline teams, first responders, will be much appreciating the fact that when there's any calamities, natural calamities, for example, to be able to react instantly. Another nice feature that we will have in the next generation satellite Hyperfield 2 is the AIS responder, which will then allow us to understand which vessels are dark and which vessels are stealth vessels. This is important because currently it's separate modality that's being purchased after the space data is being, or satellite data has been captured. So we are actually bringing these two features together to again speed up the phase where we can detect and identify vessels instantaneously. Right now, Kuva Space has launched 2 satellites. They are first generation satellites, Hyperfield 1A and 1B. This year we're planning to launch 2 more satellites, Hyperfield 2A and 2B, and the following year we'll be ramping up our satellite constellation. The second generation will be at very low Earth orbit. We're looking at 320 kilometers from Earth. And so then I will speak about, they're equally important, which is the AI side of our solution. We're natively integrating AI. You probably have picked it up, as I mentioned, that we're going to have onboard GPU. So it's no point to have the hardware if you don't actually develop the models. 1/3 of our company is made of data scientists with AI background, and of course with industry background as well. And so for just a feature, list of things that we're working towards, and some of them are already a reality today, which is on orbit calibrated data products is delivered within 3 minutes upon acquisition. On orbit multi-center data integration and delivery of alerts in less than 10 minutes. So this is the vessel discovery alerts, for example. And then automatic third-party data fusion. This is something that we're working towards, that we will be able to integrate. While the core of our offering is hyperspectral, we recognize to deliver insights that are actionable, we do need to understand how to fuse data from different sensors. And so we are actually going to develop models that will be automatically integrating this data depending on the applications and the needs that our users have. last but not least, a bit further down in the decade, if you will, as we grow our constellation, the need to operate these satellites intelligently and effectively means we would be also applying AI to the platform, the satellite maneuvering. So I didn't get into the actual camera technology that we have, this hyperspectral camera technology. In short, it has different modes of imaging, 4 different modes: scanning, staring, stereo, for example. And all of these modes need to be used at the right time. And how we're going to figure that out is through AI. When the application requires wide area scanning, we will do that. Once the application discovers there's a change in this wide area that it just can't, the next satellite will be tipped automatically using AI models to narrow the bandwidth or the wavelength that we'll be collecting. And so this is the cognitive way of operating our satellite that we're working towards. So some maybe concrete ways. I know some of you are familiar with different data levels. Our processing chain is compatible with the European Space Agency standards. So, and in fact, what this means in practice is that our data is compatible with Sentinel data. As we know, the vast majority of the products and services today rely on Sentinel data. It's important to make sure that the fusing of hyperspectral data and Sentinel data becomes seamless as well. So for us, AI is being applied all the way from frame band alignment to georeferencing to cloud detection. Just maybe an overview to bring all of this together. I spoke about satellites, I spoke about AI. How does this whole thing work end to end? So imagine a scenario where we're collecting data, a number of our satellites is collecting data, scanning, and it's processing data both in orbit and on ground. And when it recognizes that there's a change that needs to be, or there's an information that needs to be further studied, it will do so. It will do so automatically, and it will be tipping the next satellite, and the next satellite will be picking up the data in the range with the right signal to noise ratio that will fit the application that we're talking about. And then eventually, depending on the urgency of that information, it'll be downloaded either through set-to-set communication or then through the set-to-ground station. And the end goal for us is, in fact, to remove the need for our customers and users to have to manually process all this information. So what you'll be seeing at the end of it is my crop undergoing, or any part of my farm undergoing any stress? Is it experiencing any diseases? Is the water quality compromised? Is there harmful algae bloom? Is there a camouflage net that is a threat for my national security that's coming up? So these are the type of information we'll be delivering. This nicely brings me to the example use cases that we've been developing and working on. Some of them are customer pilots, some of them are proof of value, proof of concept that we've developed. So the ones that you're seeing now are very much illustrating cases from defense, civil security perspective. And so the first one is change detection. We've identified this Ukrainian-Russian border. It's very, very faint. I'm sorry about that, but there are little red dots. With the first generation satellite, we can detect change, but because the wavelength is not extensive enough, we cannot really identify it. So what we can help at this point is to help our customers notice that there's a change, and so they can then dedicate resource optimally to go figure out what's really happening, or then we can help them to uncover the change that's been detected with other modalities like very high resolution RGB, for instance. The second image is actually detecting a metal, which was invisible with optical, but we were able to notice it, again, on the Ukraine-Russian border. The third one, which is a unique capability for Kuva Space, and you probably remember I just said that with the Hyperfield 2 platform, we will have AIS embedded, which means that our speed to deliver vessel detection, identification will be world-class, in fact, and eventually we will be also enabling vessel rediscovery. So again, we're not looking at images as the way are looking at the vessels as the way our eyes would look at them. We're looking at it from a spectral perspective. And this means we are actually going to be collecting spectral library. We're going to be collecting the world's biggest vessel spectral library that would allow us to keep track and follow all the different vessels that are in different waters, contested waters, calm waters, you name it. Now we're moving into civil applications. Of course, in defense scenarios, some of the civil applications will become relevant as well. For example, the first one, land cover. Any changes in land cover has implications to situational awareness decisions that are made, as you may very well know. This is an exercise that we did with the Copernicus program, where we looked at land cover mapping. My colleague earlier today presented this in greater detail, where we looked at Sentinel data, used our AI model to study how it's picking up all the maybe 7 to 8 asset classes that we have defined for this pilot. And then we used our Hyperfield 1 data, did the same exercise, and noticed that the performance is okay, but not great. What ended up happening was when we merged the two data sets, Sentinel and Hyperspectral, into our AI model, the performance actually improved. And we actually uncovered an area where the land cover mapping was not noted with the ground truth that we used. So again, the potential is there. Hyperspectral can take us to new dimension when it comes to understanding, but also merging relevant modalities or other relevant data, other sources, will be equally important. The second use case here is about opium fields. Obviously, it's something that but a number of nations and civil authorities are keen on following and intervening when needed. And so this is an exercise we did in Afghanistan, where we discovered the poppy fields really through the spectral fingerprints, because they are pretty much camouflaged with other vegetation quite often. So what we were able to do is to identify the poppy fields through spectral fingerprint. Again, more on legit crops that are used for food, soy and maize. You can see that we've done a mapping in Argentina, and all these have been, by the way, validated with ground truth. So it might look a bit not real, the images, but they are actually been validated by ground truth. So the mapping of our AI model of different species, different crop is actually true. And then we move on to the next one. This is marine-related use cases. Bathymetry, the seabed and the environment underwater is changing quite radically today thanks to climate change. Yet the way in which we monitor these areas, underwater world, is quite slow. We have sonar beams that's being used almost on every decade, and the red line actually illustrates the way in today what we monitor or what we are actually measuring. This is Singapore Strait. So it's only that line you can understand what the bathymetry status is looking like. Whereas the big area that's being colored and it's in different shades of blue is what we've done. We were able to show the depth changes of Singapore Strait. Again, imagine when you're being able to do this, every week. Not that we would need this, but the fact that you will be able to access such information, especially in areas where changes are more frequent, it will be becoming more and more valuable. Kelp, overall hydro biomass is not really covered with satellite imageries today, and so this is another area that we are looking into. Kelp, submerged kelp. It has huge contribution when it comes to biodiversity, when it comes to carbon, blue carbon. Last but not least, water quality, identifying the quality of the water, mapping that, and also detecting and identifying harmful algae bloom. And here's our roadmap. Ambitious, yes. We were founded in 2016 at Aalto University. And this year, in April, we'll be celebrating our 10th year anniversary, which is a great milestone to reach. And you know, a lot of work ahead of us. We're now at 2 satellites. We're going to be ramping up satellites quite heavily. So all the support and ideas from the crowd is welcome. Thank you.
Thank you very much, Malati. Yes, this is working. Yes. So, excellent presentation. Do you have questions now? Da, 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 da.
Hi. Is it working? Okay. Yeah. So clouds in multi and hyperspectral images, they are a treasure to some and garbage to others, but for object detection, I guess you will need to be quite sensitive also to thin clouds, so you can effectively tell where like thin cirrus clouds are. So have you done already studies towards that? Are thin clouds a problem, or are you effectively able to get rid of them?
Yeah, one of the things our cloud detection model is now able to do is to segment different types of clouds. Though we haven't, I don't think we have done like the implication of different types of cloud to our processing. So that's something that will be coming up. But definitely being able to segment cloud is already a big progress in this area.
Excellent. Thank you for the question. So, others? I guess not.
Thank you.
Thank you very much, Malati. And I think that like seeing through a little bit of cloud, like those kind of like partly see-through clouds, I think that's a question that in many areas would help, and Hyperspectral has more to offer to kind of find the way how to do it. But thank you very much, and let's go for the next one. So it's Joe Cotti, Airbus. I think we see each other once a year. So welcome to the meeting, and tell us what Airbus is doing for the next new things.
Okay, I think you can hear me, I hope. Well, yes, 5 years I'm coming here. I see some familiar faces. It's always fun to be here. I'll keep coming back as long as you'll have me. Thank you for sticking until this time. I will be on time, I promise. So, the next evolution of Airbus capabilities. This is the topic while you're looking at Gdansk. Tallinn, why am I choosing this image? I know that people are wondering why. 2 main reasons. First of all, I do love this image because the radiometry is flawless. As you can see, there is no color spillage. It's crisp. Every detail is there. It's simply one of the best images we have acquired recently. The second reason is that I promised to someone who was supposed to be here and is not that I will put new images in this presentation. And I do promise that after this one, you will see only new stuff. Unfortunately, this person is not here. Nevertheless, I do hope you will enjoy on his behalf. So what we'll talk about, and I'm going to be synthetic about it. First of all, a very short intro, because even though most of you know me, I suspect some of you still don't. So 1 slide, I do promise, not more than this. A very short reminder on what do we do today, and then, of course, a topic of what's next, and this is the main one. And, of course, a lot of nice images. I hope you're enjoying Bora Bora in the meantime. And let's start with the intro. Space Digital is the name of the business line for which I work. What do we do in a nutshell is deliver data. That's what we do. Deliver data to users, governments, commercial entities, the kebab guy around the corner even. Potentially whoever needs data can get it from us. Potentially if you need systems and services, we can do those as well on top of the data, and all of it is packaged through a digital offering on the cloud called One Atlas. I'm sure you heard of it, but that's not the topic of the discussion today. Reminder on Pleiad Neo, this image, I'm sure some of you have seen it already. It's a favorite of mine because of the artifact in the middle, which I'm sure some of you, as experts that you are, you can imagine what it is. I'll tell you simply because I'm talking, questions later. This is the sun reflecting from a window in an image acquired 600 kilometers in space. So the telescope is so sensitive that a simple reflection generates these type of artifacts, just to show how good Pleiad Neo is. 1 slide with numbers, 1 only. No, sorry, there is a second one later. But this is to remind us Pleiad Neo. I will not go through the entire slide. The only thing I will remind is the resolution, the 30 centimeter native, and the geolocation accuracy, the 3.5 meter coming from the satellite itself. Of course, we can augment it with GCPs and other methodology. So this is what we have today, and the question is, are you ready to what are we preparing next? And there should be a video. I'm proud to introduce Pleiad Neo next. It was announced officially mid last year. Not a lot of details were available back then. Right now, I have the privilege to share some details beyond the amazing video you just seen, obviously. So, with Pleiad Neo next, we aim to be the first one entering the 20 centimeter class resolution. I cannot tell you the exact number yet. It's commercially sensitive. Nevertheless, better than 30 centimeter. HD processing will bring it even better as well. Some numbers as I promised is the second slide. We're talking about 20 centimeter class with a SWOT of 11 kilometers in total, accuracy improving from 3.5 meter to 3 meter, fully compatible with the current Pleiad Neo system architecture, fully compatible with the current ground segment of Pleiad Neo in total. It's more of an evolution than a revolution. Nevertheless, by entering this type of resolution of 20 centimeter class, we do aim to unlock new capabilities and new applications. First simulated images, I stress again, simulated. Of course, we don't have a satellite yet to show the images. However, these are high fidelity ones. We have elaborated them using aerial imaging and applying the correct filters to compensate for the space. So here is Washington, USA. Here you have another snippet of Washington. And this is my favorite one. I'm further zooming in. And here I'll ask a question. I'll challenge you a bit. Look at the cars and what is missing? Anyone? Somebody? Look at all the cars. Something is missing in all the cars, please. Sorry? Somebody said something, maybe not. Come on, who's brave? Yes. Bravo, the mirrors. There are no mirrors. Why is that? If you think of it, mirrors are objects which are much smaller than the 20 centimeter class that we are aiming at. So this is the fidelity of the simulation we are showing. This, there is one.
In the middle row.
In the middle row.
The right one. The truck has big mirrors.
Yeah, the truck have big mirrors. That is correct. Thank you, UC. So this is the point I'm trying to make. We didn't just put a Photoshop or an AI to generate these images, and then I'm showing you amazing stuff that will never happen. This is a true representation of what we expect to have when Pleiad Neo Next will be operational. So whatever is not contemplated in the resolution, you will not see, the mirrors. However, the greater detail that this resolution will provide, you can see it over there. So moving on, another one of my favorites, this is Paris, and I invite you to look at the people that you see walking in the courtyard. I had a question in another presentation of mine earlier, if you can see people and what about privacy? Not yet. I don't know if this person is still in the audience, but the concern was about people's privacy and if we can spy on people. No, we cannot yet, but nevertheless, you can see people very clearly in this type of resolution that we're showing right now. Whoops, sorry. Last but not least, I added it at the last moment. My colleagues don't like it. I actually love it, simply because if you look carefully for this type of applications, which is oil and gas and industry, you can follow particularly and meticulously each of the pipes. You can differentiate them. You can see which one of them goes where. It's not a blur of infrastructure with no details. You can really analyze every little corner of this site. So why are we doing this ultimately? We want to sustain our legacy of excellence, that's obvious. We want to penetrate new markets. We want to improve our capabilities. Ultimately, where we are today is that we have delivered 750 million square kilometers of 40 centimeter resolution. We want to improve of that. Record delivery time is 12 minutes from acquisition. This is the current Pleiad Neo system. The Pleiad Neo Next will top it, obviously. The agility we have improved and we are improving. And I want to draw your attention to the cloud-free success rate. There was a question previously from a gentleman in the cloud about clouds and how they impact images. In October 2025, we had 70% of the acquisitions cloud-free. Cloud-free meaning less than 10% cloud. So believe it or not, we can forecast in such an accuracy that 7 out of 10 images that we acquire will be cloud-free. Last but not least, we aim to improve on the delivery. We are deploying a new ground segment infrastructure as we speak, more antennas, more X-band and more S-band. Currently, this is the setup that we are using. We have antennas in Inuit, Punta Arenas, Kiruna, and Svalbard, effectively the North and the South Pole, which means that on every orbit you can uplink and downlink. We are adding 2 more antennas in the Southern Hemisphere, again for downlinking, which means that effectively, whenever an image is acquired, you already are able to downlink it immediately. I had a question a couple of hours ago from 2 guys that asked me what is the bottleneck of the system and what happens if you take too many images and why you don't compress the images. The reality is that we don't need to compress, we don't have a bottleneck because we aim to download everything that we acquire in real time. So the only bottleneck we have is that we don't have enough satellites to satisfy the market needs. Currently, we're flying at 120% capacity in some regions in the world, mainly in Europe. We need 4 more satellites to satisfy the market demands. So for us, it's not a matter of having too many images and not being able to handle them. The problem is that we don't have enough. With Pleiad Neo Next, we aim to expand our constellation. Ultimately, that's the roadmap that we are at. We want more satellites. We want to serve the market better. We want to be able to provide good data until 2040 and well beyond. So the ambition is the following one. We're still going to be flying the 2 Pleiad Neo satellites, the legacy 50 centimeter resolution. To those, we are adding the current Pleiad Neo constellation, the 40 centimeter ones. On top of those, we're adding CO3D, 50 centimeter resolution. I'm not in a position to share much on CO3D yet, but maybe if you'll have me next year, I will present that one, hopefully. And on top of it, we're aiming to have Pleiad Neo Next 1 and Pleiad Neo Next 2. Pleiad Neo Next 1 is slated for 2028. Construction is well on the way. The long leading item for Pleiad Neo Next 2 have already been ordered, which means that the construction will commence shortly. That one is slated for 2030 Q2. So with this, we aim to serve the market well beyond 2040, give or take. With this, I thank you for the attention and questions.
Thank you very much, Joe. I have an immediate challenge because the Tallinn picture is above a park where they do the disc golf festival, as they call it, the European Disc Golf Festival. So the new Neo Next needs to see a disc flying in the park wherever a contest is going on, and then I believe it's really cool. Thank you for this presentation. So, questions? We have time for one. There is one.
Thank you so much for the presentation. Question regarding the resolution. So you mentioned 20 cm, and the simulated picture you showed, you said the missing, it cannot capture what it cannot capture. That's clear. But then with the, I guess, AI technique, could it recover what was missing or reconstruct what was missing?
I'm terribly sorry, but I didn't understand the question. I'm terribly, terribly sorry.
But could you hear me?
I hear you.
Sure. Sorry. Yeah, I was asking about the image or the resolution. So you mentioned the 20 centimeter Leo Next, and then you showed the image where you asked what was missing. My question is, whatever cannot be captured with the native resolution, could it be generated with the, I guess, AI technique, which makes the resolution 3 cm?
Okay, now I understand the question better. So we aim to produce a fidelity representation of the image itself. It's 20 centimeter class, it's not 20 centimeter resolution, I stress that. The number is somewhere between 30 and 20, it's a bit closer to 20, but I cannot tell you the number. What we did is use aerial imaging with similar resolution, and then we applied the additional filters to come to, let's put it bluntly, to have the space effect and the distance effect on top. So we didn't alter the image using AI. We just took an existing image and processed it accordingly to a space environment. We don't aim to add anything that it's missing because we deliver the images as they are. We don't tamper with them, we don't add, we don't subtract. The images are as they are, and that's it. I hope I answered.
So how does the feature of improved resolution work? Like when you have a native resolution of 20 or 30 cm, and then there is the feature of improved resolution down to 3 cm. How does that?
So we have an additional feature of improving the resolution. It's called an HD process. This is not adding resolution. This is just cleaning the image a bit better. It's called HD. From 30, we go to 15. From the 20 centimeter class, we will go lower. I cannot tell you that again. But ultimately, we will not add particulars that can be seen with the new number. You're just going to have an image which is nicer. I don't know how else to say it. However, the market confirms that the HD 15 really looks nicer, but the level of details is still a 30 centimeter detail.
Okay, well, one more question, if I may ask. How many, to have, let's say, continuous coverage of a specific area on Earth, how many satellites do you need?
Well, we don't have a continuous coverage. We have an intraday revisit. We have 2 Pleiad Neo Next that are flying at the sun-synchronous orbit, polar, which means that depending on the latitude, you can get an image a day, sometimes 2. In northern Finland, even 3 per satellite. We're going to have 2 more Pleiad Neo Next and are going to fly in formation with the other Pleiad Neo. So you're looking at, depending on the latitude that you are, I hope you can hear me well because I'm not speaking to the microphone, you can look at between 2 to 4, 5, 6 images a day, potentially, when the full constellation is deployed. But we never aim to have a continuous coverage. It's not video, it's still just images.
Thank you.
My pleasure.
Hey, thank you very much. Another round of applause. We still have one presentation to go. And then there's posters. So, hey, Aku Riihelä is the next. He will talk about a climate mission proposal. And go ahead.
All right. Thanks, Mikko. So to conclude today, and I'm keenly aware that I'm standing between you and refreshments, I will be concise, but now we'll take actually a look into the other end of the scale, into the very large scale and into the climate application. So I'm here today to present to you a candidate mission that we are designing for the ESA Earth Explorer 12 that is called the Earth Climate Observatory, or ECO for short. I'm here as a member of the mission advisory group for this mission, alongside this very long list of colleagues who are also working on this. But before going to the mission, let's take a little bit of a look into why we want to do this, why this is important. So on the fundamental level, the Earth's climate system is governed by 3 interplays of energy. We have the input of energy from the sun, which is the total incoming solar radiation that's coming in there from the left. That is the input of the primary input of energy into the Earth system. A part of that energy flux is being reflected away by the Earth, by its clouds, by its oceans, by its snow and ice, by its forests, the entire Earth's atmosphere and surface system. And then we have the thermal emission, which occurs, let's say, primarily during the nighttime, in which the temperature of the Earth and its atmosphere causes it to radiate energy in long-wave radiation away from the Earth. And the balance between these three factors, if you have a system that is in climate equilibrium, will equate to zero. However much energy the Earth gets from the sun, a part of it, it reflects away, the rest of it, it emits away, and the system remains in balance. But when you have a case where the system is not in balance, as exists today, then you have an Earth energy imbalance. So whatever is coming in from the sun is not all being reflected or emitted away from the Earth. So the Earth system is gradually accumulating energy. What happens to a system when it is gradually accumulating energy? It begins to heat. And this is the fundamental driver behind Earth's climate change. And the EEI as a variable, in a way, represents the climate forcing that the Earth system has not yet responded to, but will in the future. So when you have the energy imbalance, the Earth reacts by heating up so that it emits more long-wave radiation, more thermal emission away. If you again perturb the system so that you perhaps disturb the long-wave radiation, let's say through greenhouse gases, this has the capacity to then push the system still further away from balance so that the energy imbalance increases. So understanding EEI is at the heart of our understanding of the climate system and where it is going. The figure here is from a study by the mission team, Thorsten Mauritsen and others at Stockholm University, where they looked at the temperature, global annual mean temperature projections from the SSP 2.6 scenario there on the blue. The SSP 2.6 is let's say, a successful climate scenario where we more or less managed to stabilize the Earth's temperature increase to below +2 degrees relative to pre-industrial. So you can see as you go towards the end of the century, in this scenario, the temperature peaks and then stabilizes. What is interesting, if you then look at the same in the Earth energy imbalance context and domain, which is the red curve, the EEI in this scenario will balance and begin to decrease decades before the actual temperature stabilization occurs. So if we are able to monitor effectively EEI and keep looking at it from year to year, we will be able to tell if the climate change is stabilizing or not several decades before the temperatures begin to stabilize or decrease. So this is something that is very actionable in terms of the global climate system and indeed for let's say, the global society as well. The problem is, of course, that this is a very tough nut to crack from the monitoring point of view. On an annual mean level, we get about 340 watts per square meter from the sun, and the reflection and thermal emission total come to about 339 watts per square meter. So the signal that we are looking for, that we need to measure, is on the order of 1 watt per square meter on a global annual mean level. That's measurement precision required is better than 0.3%. And this is why this is such a tough nut to crack. We are looking for a very small difference between two large energy fluxes. We currently have missions that are able to do this to some degree. The Americans' Ceres instrument has flown on multiple satellites, and it is arguably nowadays the best sensor that we have for trying to estimate EEI. But The Ceres mission has very limited spatial resolution. The data products are usually provided at about 1 degree resolution, so about 100 kilometers in the spatial horizontal domain. And while the Ceres is able to track the trend of EEI quite well, the magnitude is a much harder problem. So the raw, let's say, the raw Ceres data products usually come and the Ceres team then does some additional calculations looking at the ocean heat contents of the global oceans to bring that number down to then about the 1. Let's say. So there is a complex inversion that is required to derive EEI out of the Ceres data. And furthermore, and very worryingly, we have no guarantee of continuity in the 2030s. The present fleet constellation of Ceres sensors is aging. They will be dropping out. And there is one plan for a single follow-up mission called the Libera in the US, slated to launch quite soon, actually in 2027, if I recall correctly, but it has a nominal mission lifetime of only 5 years. So in the early 2030s, we might be looking at a case where we have degraded or even no capability of estimating EEI. So therefore comes in ECHO. The mission goals that we set out for this mission candidate is that it needs to be able to measure the EEI globally with an goal accuracy of 0.3 watts per square meter. And this is a very tough number to achieve, I can assure you. On top of being able to measure the EEI itself, it needs to also be able to look at the constituent parts. So the reflected solar radiation, the emitted thermal radiation, and also the total with an accuracy that is stated as a goal of 0.7 watts per square meter. If it can do this, then we will be for the first time able to directly measure the Earth and hopefully be actionable information for the global community when it looks into what mitigation options are still required to address climate change. Do we need interventions? If we do need interventions and we are prepared to do them, what are the effects? ECO can still monitor the system no matter what your options and choices are for addressing climate change. Here is the basic mission concept. So we want to build and launch a satellite in LEO orbit, or actually a constellation, but I'll come back to that in the next slide, which features up and down looking radiometer pairs, identically designed, one of which will measure the incoming solar flux, and the other one will measure the total radiative flux coming up from the surface in the broadband domain. So both short and long wave, everything together in one measurement. Collocated with that will be a set of multispectral cameras which will cover the same domain. And the really big thing here for ECO is that both of these, the radiometer and multispectral imager, will need to have an instantaneous field of view of about 6,000 kilometers, so about 140 degrees, so that the entire viewable Earth from low Earth orbit of about 700 kilometers height in the nominal sense will be captured by every single observation as we go forward in the orbit. And this is the key thing. So the entirety of the Earth system will always be, or at least the Earth viewable part of it, will be available in each individual observation, both the surface and the atmosphere. So the height and the FOV are designed so that both the surface of the Earth and the emitting atmosphere will be covered by the measurement area for each individual measurement. The system is designed so that the satellite will periodically rotate so that we can compare the calibrations, because this is a very, very difficult calibration problem, and we need to be able to monitor corrections can be applied to bring the precision to a higher degree. The baseline concept also calls for spare radiometers, which are normally turned off. Aperture and, if necessary, to replace them. I mentioned constellation, and that's a very key design parameter. So if you imagine that you had only one satellite, if you place that in sun-synchronous orbit, you're always looking at just one part of the diurnal energy cycle of the Earth, and that wouldn't get you very far indeed when you want to measure EEI. But it turns out, based on the simulations by the team, that having two satellites in roughly orthogonal orbits with an 82-degree inclination would allow the satellite coverage to precess around the Earth so that you would measure the total diurnal cycle of EEI once every 3 months, which over the course of a year then means 4 full rotations, which is a nice even number that is needed for the final EEI estimate that we're coming up with. The design calls for a minimum lifetime of 5 years, so we would get 5 numbers in the end out of those final global annual mean EEI. Sorry, I'm a bit too close here. But the constellation size is very important here. So we really, the MAG calls for 2 satellites to be launched here as the Earth Explorer 12 Eco mission that is really needed to bring the sampling errors down to a level which allows us to really reach for that 0.3 watts per square meter accuracy. There is a multispectral imager there as well, and I will go a little bit quicker here. So the idea here is that the multispectral imager can break down the building blocks of the radiative fluxes through multi-angular views that can be combined and constructed. So you go from radiance to flux by not applying a directional model for each individual observation, but you aggregate the different angular observations and get a flux for a particular point in the Earth system in time. And this then allows you to look at cloud-radiated processes, aerosol processes, changes in the surface albedo, which is close to my heart in particular. And this is the other side of ECO, the second half of the mission. How you design this synergy is very crucial. So you need to have a substantial set of measurement channels. I can't really give you exact details on what are to be designed because that's the industry side. They are looking into this right now, the consortia, but I put my name in some papers that says that I'm not supposed to tell you stuff at this point quite yet, but rest assured the details will be coming. But let's say the baseline called for having red, green, blue, plus near-infrared channels on the shortwave side, and then let's say 6 channels on the thermal infrared side, which covers the main parts of the spectrum, so that you can then connect these to each other to get the imager side of the total broadband radiometer coverage. And the idea is that we will be able to use this very precise radiometer to also intercalibrate and calibrate the imager data so that the imager data also reaches a high degree of fidelity. Maybe I won't go into too much detail on the proposed data products. The idea is that each one of these 3 radiative flux products gets its own treatment. Then, of course, also from the imaging side, you get these radiance data that are combined into the fluxes, which are then further aggregated into the temporal domain, into the spatial domain. And then at the very, very top level, you have the annual mean EEI over the globe, which comes out of our constellation. And that is really the key number. A few words to finish about the Earth Explorer 12 context, if you're not so familiar with this. So the Earth Explorers that ESA has built are really driven by science. So every one of the EE missions has been designed to crack a problem that has before that been considered very difficult or nearly uncrackable. For EE12, there are currently 4 candidates in play. ECO is one of them. We have also then CryoRad, which is a radiometry mission for the cryosphere, Hydroterra, which is a SAR mission for the geostationary orbit, and then Keystone, which is designed for the atmospheric composition of the middle atmosphere. But obviously, I won't go into those details today. I'm here advertising the other side, as you might understand. So we are now in phase 0 for candidate missions. We are in the middle of doing the first industrial studies, crafting the requirements, going through the design trade-offs of what can be done at what cost and how that fits within the programmatic envelope. This will continue until July this year, and the important thing for you, if you're a member of the science community, there is a user consultation meeting that the ESA will hold in July, where people are encouraged to attend, to ask questions to the mission teams, hopefully voice your support to a mission that you find the most worthy. And based on the mission review and that meeting, then the Advisory Committee on Earth Observation will make a recommendation to ESA after the meeting, which will lead to the selection of 2 candidates out of these 4, which will continue forward into phase A and beyond the studies, so that then the 2 will eventually become 1, which gets built and launched in 2036 to carry out its mission. And with that, and the final closing slide, which gives you hopefully a picture and a message to keep in mind going home, I thank you for your time.
Thank you, Aku. In the interest of us not missing the poster session start, if you have questions to Aku, you have to grab him, and the poster session kind of go up to it. And thank you very much for this day, and tomorrow there's more. Welcome, and yeah, thank you for the day.